Hello, I'm Roy Ogus, and today is December 6th, 2018. I'm here at the Computer History Museum in Mountain View, California with Robert Garner, who has graciously agreed to be interviewed for an oral history. I've known Robert for many years. We first met around 1977 when Robert participated in a digital design class that I was teaching at Stanford University while I was involved with my postdoc research. Following that period, Robert and I have worked together on several product development activities at both Xerox and at Sun Microsystems. We worked together as designers in the Xerox team in Palo Alto that developed the Dandelion workstation, which of course later became the platform for the seminal Xerox STAR Workstation product. Then a few years later, and actually by coincidence, we worked together again as part of the Xerox Sun Microsystems Sun Dragon team that developed the Sun SPARC Station products. We'll hear a lot more about these activities in detail during this interview. So Robert, we've had a long history together, and I'm delighted to be talking to you today about your story. Thanks so much for joining us. We really appreciate it.
Well, Roy, before you start your first question, I wanted to say I did work for you short time as you were my manager, and you were actually the best manager.
That's right, you were actually my manager as well, yes.
Well, it could have flipped, but you were actually the best manager I've had. So.
Okay, thank you.
And,
that's
so
right, the first part of the Xerox thing.
Yeah. And thank you for agreeing to do my oral history.
Okay, my pleasure. All right, so why don't we start at the beginning? Can you tell me where you were born and when, and where you grew up? At the same time, why don't you also tell us what your parents did and how they influenced your various career decisions?
Yeah, well, those are all the easy questions.
Yes.
I'm a native Californian, actually. I was born on the vernal equinox, 1954. That's when the day is half light and half dark. My parents lived in the it's the Manhattan Beach area in LA, but when I was 1 year old, I ran away to Arizona. What really happened is that the companies were being encouraged to expand inland because of the threat during pre-World War II of invasion from Japan. So the company that my father worked for decided to move inland to Arizona. My father, he grew up with a lot of responsibility early on. I think he taught that to me. When he was a young kid in high school, he used to drive all the kids in the high school bus to the high school in Hollister. He would drive down Highway 25, drop them all off, stay at someone's house by candlelight, do homework. Next morning, pick them all up one by one as a freshman in high school before he could even have a driver's license, and drive all the kids into school. He wanted to become an aeronautical engineer. His goal in school was to find a crashed airplane, because you couldn't afford to buy one, and restore it and to get it to fly again. He ended up joining Air Research next to the Sky Harbor Airport in Phoenix, and worked on gas turbines his career. He kept all his college textbooks, and so I ended up devouring his physics textbook. I just loved all the stuff I saw that. Where I grew up first in downtown Phoenix, and it was orange groves and being converted into housing divisions, and we used to make things, build tree forts. I would make all kinds of contraptions. I was known for building things. As a young kid, you would find strange things like algebra papers thrown out of cars, and I was totally fascinated by those. Camera lenses in the field, all kinds of crazy things. I even later learned that Spielberg lived in my neighborhood, so it's even possible that I played with him as a young boy. And we certainly went to the same restaurant he did his first movies in. Starting somewhere in grade school, we formed two of my best friends and I formed a science club. And we met every weekend. We did crazy things. We built 3D chess sets. We built tube-based amplifiers. We did mathematics. We found adults who had access to computers. So we started writing small programs in 7th grade, 6th and 7th grade. I think I wrote a tic-tac-toe program. You would kind of hand the program over to some adult and they would go find a computer somewhere to run it for you. so the two friends of mine were Jerry Jenkins and Chris Beall. And Chris Beall was a brilliant person who, I'll never forget, he wanted to check out a college physics book, but they wouldn't let him because they thought he was too young, and he was trying to design a particle accelerator. And my friend Jerry Jenkins was a brilliant mathematician. And we got access to a terminal system at the high school first that did time sharing to a scientific data system, SDS Sigma 9 computer, or Sigma 7, located at a service bureau in downtown Phoenix called TransData. And that's where you you learn that if you actually go to the computer center at night, you can get full access to the computer. It runs faster at night. They let us run the whole machine ourselves, like at 1 a.m. or 2 a.m. Quite a fun thing to do. Also, we found that if you search the waste paper baskets, you found user IDs and passwords. So we could get extra free time on the computer and get privileged accounts, because even then people didn't realize they shouldn't be typing out their passwords. Back to my father, I guess, a little bit. He loved the outdoors, and we did a lot of hunting, and he was very observational. He could see animals before I could, and so he really taught me the skill of being a careful observer and watching things. And I was really into botany and nature, and I would devour things like science news, and I couldn't figure out how people got their ideas, so I figured, well, maybe you had to study things, so I would take pictures of landscapes to see how they might change over time. My dad would take me hunting. I used to go deer hunting. I later realized that wasn't the great thing to be doing. He had a playful, wry sense of humor. We went on car camping trips. We visited Lowell Observatory. Arizona has all these observatories, islands in the sky observatories. And I'll never forget being impressed by seeing Percival Lowell's hand drawings of the canals on Mars. You know, he so projected into what he was seeing through his refractor telescope that he thought he saw canals. But seeing those original documents just really moved me into doing science and in the history of science. Also in 7th grade, I got a little carried away, and my social studies project ended up being 700 pages of histories of the conquistadors and the Spanish of the Southwest. I was the school class president in 8th grade. I gave the graduation class speech in 8th grade. Oh, I almost forgot, in 3rd and 4th grade with my friend Chris, we were school crossing guards, which is a very responsible position. And in 7th and 8th grade, I had the responsibility of lowering and raising the flag on campus. So I had these very kind of responsible things to do. But that was the time of the Vietnam War and a lot of protest against what was going on. I tended to kind of hang out with the people saying, let's end this war and stop this craziness. So I had kind of an anti-large establishment mindset, more of the hippie mindset, you could say. So I wasn't really interested in business, but I was more interested in science and technology. My mother, the last thing on my father is that well, at that time, I guess, I also joined the Boy Scouts. We went on a lot of backpacking trips in the desert and the mountains in Arizona. I eventually became an Eagle Scout. On the way, you do things like Order the Arrow, where they do unusual things like you don't speak for an entire day. You know, what's it like to go through an entire day without speaking? One of the things that came from joining the Boy Scouts was I attended the International World Jamboree in 1972, which was held in Japan and at the base of Mount Fuji. And that taught me that you could just walk, 100 yards and be with another group of people from around the world, which also strengthened my interest. I guess something else I hadn't mentioned is that at the time, Heath kits were very popular, electronic kits where you would build things. So I hand-assembled my family's color TV from a Heath kit. Through following the instructions, I hand-assembled a shortwave radio, and you could listen to people from around the world with the shortwave radio late into the night. You could listen to programs from Russia, Cuba, South Africa, and around the world. And so my father and I actually continued our backpacking tradition as I became an adult, and we used to go backpacking into the canyon countries of Utah and Arizona and New Mexico. so I was very close to my father. My mother was raised on a small farm in West Virginia, and she was very caring and inquisitive and believed in science. She really believed in science. And she used to, when she would go shopping, I'll show you how geeky I was, she would drop me off at the library, which I just loved, and I would spend all day at the library reading books on relativity by Einstein and math and all these physics things. I was just in heaven. I just loved the libraries in the Phoenix area. As a student in high school, I used to go to the Arizona State Library and hang out in the stacks late at night, and that's where I got acquainted to all the books on computer design. I guess I did the usual science fair projects. I think I did the electrical activity of fish. And there you saw kids doing little simple computers as science fair projects, and I found them to be too simplistic. And you know, if I have access to a real computer, why bother building something which isn't very functional? So later we moved to the North Scottsdale Desert. This would have been about when I was in 6th grade. And there we lived in the desert but near a golf course. And so that's where I got into running. It was a very meditative thing. I would run the courses at night through the sprinklers when it's over 100 degrees outside and jump into the pool. I was a lifeguard at that pool, participated in swim meets, and it was a great balance between exploring the creatures of the desert. I had snakes. I used to collect snakes. We had snakes in the house. Terrified my parents when they would escape from their cages, and my father would find a snake going down the hallway in the middle of the night. So I have a very strong interest in the outdoors and in natural history.
So maybe I can just ask a question. So it seems like many of your activities were technically oriented. I mean, your father was in the technical field. But you also did a number of other activities that were not technical related. But somehow you kind of moved towards a technical career. And in fact, you told me that your father actually moved you from doing a natural history type of university education to an engineering one.
Yes.
So
yes.
Do you really understand how your interest in getting into the computer field evolved? Was it just innate, or was it your influences while you were growing up?
Well, I think I was interested in electronics, and I think it was the access to the computers, early access to computers through parents. I think at a very early age, I realized that computers could be used to control almost anything mechanical in the world, and it was a hobby, you know, designing electronic things. I consumed every issue of Popular Electronics. Never forget the Altair cover, you know. But my allowance didn't allow me to purchase the kit. So, also in high school there was the experience of the International Boy Scout Jamboree, but also I took Saguaro High School, where I went. I actually ran for freshman class president. Mike Boych, the friend who had also involved in our science club, beat me. But it was a Sputnik era high school in the sense it was well funded. The math teachers were incredibly excellent. The physics teachers were incredibly excellent. I was a TA for the physics teacher one year. We actually, the joint set of us at the high school placed 4th place in the national MMA national math exam. And the high school before us was this place called Palo Alto High, which we hadn't heard of before. So it was, and I took Russian as well. Russia was dominating the news, Sputnik and all the spacecraft, and it was thought to be important to learn Russian. So I took Russian in high school, and then I visited Russia in a foreign exchange program, a language foreign exchange program, during the height of the Cold War. In fact, I was in the consulate in then called Leningrad the day of the American bicentennial. It was quite an experience. I remember one thing about Russia is they really promoted science and technology. So as a geek, it was kind of fun. I remember going to a science show in Russia featuring the rockets and stuff and the Soyuz and their cosmonauts. And there was a computer, and it looked a lot like an IBM 360. I mean, later I learned that they cloned 360s almost directly. One thing I think that really helped was I took a typing class as in grade school. And so therefore a teletype terminal was not intimidating. You know, many people in the computer business never learned to type, but by taking a typing class first, that made that less intimidating.
And was it really true that you were thinking of doing a natural history college? We can get into your college next.
Yeah.
But
well, even before I get to college, one of the other projects I did is I built the Scientific American have an amateur scientist section, and I consume that every month. And one day I decided to build one of the projects, which was a mass spectrometer. And I linked up with a physics professor at Arizona State. He helped me build it. He called it the best plumbing system in the world because you have to have a vacuum in them. And it's a very simple mass spectrometer, but that was a lot of fun. In high school, I used to borrow the physics teacher's Geiger counter, and I would inject radionuclides in plants. You could actually get samples of radionuclides over the mail by subscribing to free U.S. government publications because I couldn't afford them. And I would inject them into plants and see how they might travel. Again, my interest in. The other thing that happened in high school that really led me to computers was GE had a recycling center in South Phoenix near the airport. And at this center, they would take all their defunct computers, maybe just 1 or 2 years old, and tear them apart. These giant mainframe computers, GE 225s or whatever, they would chop off the ends of the printed circuit cards for the gold, and they would sell the disk platters as coffee tabletops, and then they would take all the discrete components and make them available to hobbyists. So we would go visit the GE recycling. So that probably was my earliest interest in old computers as well, because how could they be chopping up old giants into pieces and selling them as coffee tabletops? The disk drives, 4 feet in diameter disk platters. I never had enough money to buy one, but and there were other old collectible places in town that had that kind of stuff. I was also very much interested in math, and I remember in high school I was really fascinated by Gödel's incompleteness theorem and math philosophy. But I really did, like you say, I really wasn't sure whether to go into natural history or engineering, and my father said, well, you'll get paid a lot more doing engineering, and that led me to pursue that. So I went to Arizona State. My friend Jerry Jenkins had already started there. At Arizona State, you had to, I wanted to get a BS in electrical engineering, but they had a BS in engineering degree. So you had to, EE would be a specialty, so they made you take a well-rounded engineering curriculum.
This was 1972.
1972, yeah, when I started at ASU. I didn't like the fact I had to take mechanical engineering classes necessarily, but it really helped me later in systems design, understanding things like fluid and heat transfer and stuff. They did allow me, so I got 2 jobs. I found that taking undergraduate classes, especially from maybe perhaps not all inspiring teachers, was a grind. And I think what really helped me get through college as an undergraduate was I was able to get 2 jobs. One was for a math professor, Dr. Gregory Nielsen, and the other was for an experimental psychologist, Barry Lesowich.
So these were during the term time. They weren't like a summer job.
They were during the term. They were during the term. So Dr. Nielsen had an office in the math department, and he had a Tektronix 4010 terminal, which was a storage device, and he was doing 3D surface, one of the very earliest 3D surface drawing programs, which was based on parameterized X, Y, and Z as a function of U and V. We ran the code on a PDP-10 located in a time-sharing service and over a 300 baud modem, and would come the coordinates for the 3D surface, which would show up on the storage tube. And I hand-tuned some of the algorithms in assembly language, so I learned the PDP-10 assembly language at that point. Most of the software was written in a high level, I think it was Fortran. And I did a special project for Greg. We realized that we could take the 300 baud modem coming over the phone line, record it on a reel-to-reel tape recorder at slow speed, and then speed up the tape recorder and get a faster graphics, like 4 times rendition. So I built a little box that converted the sound to levels that were appropriate for a magnetic tape recorder, and that was a lot of fun. I also had the honor had access to his office at all hours of the day, so that's where I went and did my homework. So I could avoid the dorm room life and retreat to the math office on Friday nights. And then Dr. Barry Lesowich had a real-time system, a DEC PDP-15, an 18-bit computer, and eventually he had 2 of them, and it was used to send auditory signals into a soundproof room one of those rooms you walk in and you can't hear due to all the cones. And you know, it was a thing to do those days in experimental psychology to determine how the human head detected distance or location for things. So you would send sounds into the students in the room and they would be the guinea pigs. The technician of that, well, you know, again, this was an experience that really formed me a lot, which was, you know, these computers were human-sized. They're in racks, and they're mute, but they're smart. You can tell by the blinking lights, you know. So as a kid, you're walking around these big computers with blinking lights, and it's a pretty impressive experience. And I think that really formed a lot of feelings about computers at that time because they were human-sized.
And so your degree at...
Well, let me finish on the PD-15. So the technician, Woody, I noticed several things about that. He was kind of a crazy guy, but he kept a Bible on top of the system, and then we recorded, when it booted up, we recorded a Good Morning Woody song on it. And so just imagine that this system in mid-1970s cost probably $150,000. Today's dollars, $700,000, $800,000, also $1 million. It took that kind of system just to play, 5-second audio. So it was kind of hard to extrapolate from there. And the campus also had a UNIVAC 1110, which was a large business computer, although the astronomers in the math department would complain that it would never get the same answer on floating point calculations. So I was really learning how computers could be fallible and not necessarily give the right answers. A friend of mine on the UNIVAC 1110 was able to become super user and take over command of the user console right during the middle of a demo that someone was giving to visiting dignitaries. And the guy freaked out and thought, because we had a big eye that blinked on the screen, took over the screen and an eye blinked. He just about freaked out.
So talking about UNIVAC, you said you told me you did a summer job at Sperry.
Oh yes, yeah. One of the jobs that I had was in the summer, just a summer job. They had an HP 2100. This was Sperry Flight Systems. So while in the room next door they were encoding the words pull up in different voices, for the pilot to pull up. In our area, a person had written a compiler. This was the era when people debated whether compilers could generate good code, and it didn't fit in the memory. So I had a summer job to be a human compiler. I would take the assembler output and rewrite it into a smaller form. And I could see how dumb the compilers had been. So that was a great learning experience on compiler technology.
Were there any other summer jobs you had that were kind of similar type of experience?
No, but I do remember a physics student there was living in the math department who wanted to build a TV terminal, that would display characters, and he couldn't get it to work. And I was surprised that somebody with a physics degree didn't understand the practicalities of building circuits. So I helped him get his master's degree. So yeah, that was so I basically got through. One thing that was really nice though is the engineering department allowed me to take math courses instead of engineering math courses. So I could take courses in the math department, which was really nice. So I applied to universities. I applied to several. I was so delighted that Stanford admitted me. I didn't realize that by going to Stanford, I'd be kind of coming back to where my father had started in California. But I applied. I guess I did one other project there at ASU. I did an A to D converter, which really taught me about, D to A converter, which taught me about that transition. But for Stanford, I got admitted in information theory, as information theory.
So did you consider other universities as well?
Yeah, I did. I was accepted at some others, Case Western and a few others I can't remember now. But
so you chose Stanford.
Yeah, one thing I liked about Stanford is they had a very short master's program, just 1 year.
1 year.
Okay. And that really appealed to me because I really wanted to get out into the real world. And I'll never forget other people like Andy Bechtolstein, who was a student there. He really wanted to get out in the real world. Of course, Bill Joy, who at Berkeley did. So I was admitted into information theory, which I just loved, but then I realized it was kind of a tedious subject for a year, and I asked permission to switch to computer science, which they allowed. And they had a lot of labs, and so it was a lot of work. And I also took Russian again, which was probably not a good idea because it didn't help my GPA, because I don't think I got A's in that class. But it did teach me about the beauty of the Russian language and poetry. Political Russian sounds very hack-eyed, but since the Russian language, you can put the words in any order, it makes for beautiful poetry. And I'll never forget that. So my professors that I definitely remember were Bernard Woodrow, who really understood analog computing and had his own models for neural nets. John McCluskey, who you remember, Roy, I'm sure.
He was my advisor.
You know, your advisor, okay, who did all the Karnoff maps, and really, this is where your brain actually does what's all done by software today, but minimizing schematics and logic gates. Jim Clark I had on discrete math, who later did SGI. I had Nicholas Firth on my compiler class, and I always thought it was a step backwards when I went to Stanford because they had some IBM system with punch cards. And I actually had to write my compiler on punch cards. And I thought, for a well-known university, this seems really backwards. I was just struck by how backwards that seemed.
You probably came into contact with Don Knuth
Yeah,
as well.
I had Don Knuth for a class. I signed up for his class and I attended the first 2 sessions, and Stanford allows you to drop after a week or so, and I realized it was going to be so much work that I couldn't do it. So I actually dropped the class. And a few years ago here at the museum, I actually had dinner with Don, and I said, Don, you know, I signed up for your class and dropped it. I felt like it was 2 classes in one. He said, that's right, I did create it as 2 classes in one, so at least I felt off the hook a little bit. And then I had electronics labs. Roy, you were my instructor in the electronics lab. I think I built a 3D clock based on a cube with the since there are 12 edges and 12 hours in a day.
And you said you still have that device?
I still have it, yeah.
So you inherited the gene from your father to keep everything,
To keep
right?
everything, yeah, I guess so.
Yes.
Yeah, that's a good point. So where I stayed my apartment mates were in the OR program, Operations Research at Stanford, Rick Beanwig, and Lynn Weber and Linda Duvanovich. Lynn was a brilliant person, National Bridge Championship. Rick was brilliant. He helped me with my math and physics. I met my wife, wife-to-be, a girlfriend, at a Keystone concert where members of the Grateful Dead used to play, and I was there to see Any Old Time String Band, and she was there to see Any Old Time String Band. I was there to see Peter Rowan, and then Larry Tesler likes to say he matched us up. But I was itching to get out, and there was an on-campus interview by Bob Metcalfe, he was kind of like, oh, why don't you get out of that easy school stuff? I'm thinking, easy school stuff, and get to work. I think he was impressed by my work I'd done for Dr. Nielsen on the analog device. So what I like to say is my bike route shifted from biking from the apartment I was in from Stanford about a half a mile to the east to the campus of Xerox PARC at 333 Coyote Hill Road.
So what was it that attracted you about the SDD, the System Development Department?
Well, yeah, so in 1977, that's when I finished the degree and started working there. Bob hired me to work on Ethernet. The plan was to commercialize the Alto and to commercialize Ethernet. And at that time, the plan was, Chuck Thacker, well, the Alto, I won't go into much of the history that's been covered so much, but Chuck was one of the co-designers of the Alto. The second system after that was called the Dolphin, or D0, and as part of that system, they needed an Ethernet controller. And so my first role in SDD, System Development Division, was to design the Ethernet controller for the Dolphin. And that was a real eye-opening experience. So the Alto was a microcoded machine. You really kind of needed to get your hands dirty at that low level so you could actually implement things like bit blit to move arbitrary rectangles on the screen quickly in microcode. But also the vision that came from the Alto was that device controllers could be mostly microcode. All you needed is a minimal amount of hardware just to get the bits in and out, kind of bit level timing, but everything else could be done with fast microcode. The Dolphin, so that was the Alto vision. The Dolphin expanded upon that, but it was what you call the second system syndrome. We'll do everything the Alto wanted to do, but better. So Chuck, wanted to kind of spruce it up and polish it a little too much, and
so all this work was being done while you were reporting to Bob Metcalfe in his group, or were you actually in a different group at the beginning?
I don't recall who I reported to right from the very beginning. It could have been Bob. Yeah, I think it was Bob.
Okay.
Yeah, I'll have to get the org charts to see.
Yeah, you told me you were so amazed when you came to Xerox that everyone had an Alto on their desk.
Yes,
which
yes.
of course was very different back then.
Yeah, I mean, if you think about it, they gave each engineer an Alto, and an Alto back then cost around $16,000, and in today's dollars, that would be something more like $50,000. And so to give each engineer, including a kid out of college, a $50,000 tool is pretty remarkable, I thought. Almost half the price of a home in Sunnyvale. And I wasn't so impressed by the bitmap screen, but I mean, I was impressed by the fact they were willing to waste half of all memory on the bitmap screen. I mean, Alan Kay had proposed this, a 600 by 800 display, bitmap, half of all memory, just to make something look beautiful. You know, what's this all about? You know, so it was. But the Ethernet, I was totally smitten of. You know, Bob had been inspired by the AloaNet in Hawaii, and you know, the idea was just do AloaNet on a coaxial cable. The first Ethernet had been done at 3 megabits per second by Dave Boggs and Bob Metcalfe. I'll never forget doing my first FTP between two Altos, and like the files transmitted instantly. And if you're used to 300 baud modems, 300 characters per second, 3 million characters per second through a simple command line interface was shocking. So it just really blew me away. Of course, when I first came on, I couldn't believe they actually paid you for doing your hobby. This struck me the most. Oh yeah, this is pretty cool. This is all fun, and they're paying me. It was like $22,000 per year salary, which, you know, equivalent to 4 times that today. So System Development Division, or SDD, was co-located with PARC at the time. So we kind of felt we were part of the PARC pantheon, even though I didn't technically work for PARC at the time. We shared office space. We got to know all the people. You know, the people there were, you know, I've said before, it was like you were in some altered state of reality, but everyone there was an expert. You know, Roy, you might remember that. There were kind of this set of wizards who were very generous, kind, unassuming people. The people who fall into that camp are people like Bob McCrite, Ed Taft, Bob Sproul, Silvera Ornstein, who also did the social responsibility, Scientists for Social Responsibility organization, who was also a caver. Will Crowther, who had written Adventure, the caving game that everybody played. Ken Peer, John Warnock, Hal Murray, Steve Purcell, Don Charnick, Larry Tesler, Carver Mead, Chuck Geschke. These are all very kind and unassuming people, and just great to be around. Alan Kay was this wild, inspirational, contrarian, and practical man. I mean, that famous phrase, the best way to predict the future is to invent it, that he's, you know, now embodied on the floor at the Stanford Engineering Building. He said that when he was really angry at the Xerox planners who came to his office and said, well, what's the future going to be like? He just got so angry. Well, don't stop asking me that. Just give me the money and we'll invent it.
And that's one of his famous statements.
Yeah,
right?
well, it came out of being frustrated. I remember him being really frustrated with these planners from Xerox East Coast, and they had no idea what was going on at PARC, really. So then there were kind of the high priests, I call them, these people with very massive and significant egos. Very brazen, unreserved, and frank and scrupulous. There was Butler Lamson, who was loud and had a huge laugh and encyclopedic knowledge. You could walk into the PARC cafeteria and you knew he was there because there was a crowd of disciples around him. I don't know if you remember that.
I remember. I also remember that we used to measure the speed of talking by how many micro-Lamsons they were.
Micro-Lamsons. Yeah, he was too smart. He was the Lord of Dealer, which was the forum where you sat in beanbag chairs and people gave talks, and you'd think it would be relaxing, but people just shot you with bullets in front of the beanbag chairs. Chuck Thacker was an intense, brilliant man, always happy to challenge you with a new puzzle. He had kind of a crooked smile and a laugh. He smoked. That was something we didn't think about back then. And then Bob Metcalfe, one of the most remarkable people I've known and worked for, a very vibrant imagination, very strong-willed, had a wry sense of humor, rebellious, political, inspiring. He was willing to, you know, being part of a big company like Xerox, everyone felt they created our own kingdom. You know, it was a castle on the hill. Bob Taylor, everyone He was their disciple. He was a very strong-armed, paternalistic. He had a mischievous laugh as well. One thing I note about PARC is there was kind of the free-thinking radicals and hippie-likes on one side, and there was the conservative, more traditional but brilliant people on the other. And I think the tension between the two groups at PARC helped for success. And I think I noticed later over years that the most successful companies or groups had a natural tension between these two ways of thinking. It was certainly present there.
And one thing you told me was you felt that both STD and PARC, even though they were part of a very old traditional company, really gave you the feeling of a startup
Yes.
culture there.
Yes. Yeah, we felt like, everyone felt like we were going to change the world. I mean, this is 1977, all there are is character terminals and punch cards. And here they had created, the people at PARC, starting in 1973, created an environment with WYSIWYG graphics, email, laser printers, everything in place. And it was just, I would take printouts of, let's say, Russian poetry and show them to someone, and they would say, "How did you generate that?" We all knew we were going to change the world, and we didn't realize we were ahead of ourselves, and we were ahead of the market. But
well, they were right. It just took a little longer than they planned.
Yeah, unfortunately. So my job, like I was saying, was to design the first commercial Ethernet. It was then called the Xerox Wire internally. It wasn't. The experimental would have been called Ethernet, but the project code name, Xerox wanted to keep it to itself, and so it named it Xerox Wire. It would be this information outlet, like a 220 plug, 120 plug outlet, was the vision. The initial goal for Ethernet Bob had was 20 megabits per second, and Dave Boggs, who had co-designed the first Ethernet, said really the best way to do it is have a separate transmit and receive sections on the board where a packet can kind of sit there ready to go, and a packet can come in. So I did that. VME-sized board for the Dolphin, about this big. I don't have one anymore. And one half was transmit, one half was receive. But the problem was, since you have to place all the TTL components on the board, is they didn't fit. And on my desk was a Fairchild data book one day, and I opened it up, and there was a 10 megahertz CRC chip. So I went to Bob, and I said, "Bob, this doesn't fit on the board at 20 megahertz." I even went to the Stanford Library and investigated ways to do CRCs differently in parallel instead of serial, and all this kind of stuff. Today you would just Google it on the web, and I said, "Bob, there's no way I can get this to fit." And I said, if we use this 10 megahertz Fairchild part, it was an F9401, it will all run at 10. So that's why Ethernet ran at 10 megabits per second. And also, Ron Crane, who was doing the analog, there was a DC collision detect, and at 20 there was a bit too much reflection from the taps.
Right. I remember there was electrical issues.
Yeah, and so that helped push down to 10. But 10 was still so much faster than anything in the world. It seemed ludicrous we were going for 20.
Yeah, we might note that the Alto Ethernet was 2 point something,
almost
which
3.
was the clock on the Alto.
The clock,
which was nothing magic
at
that number.
It was 2.96 or something like that, So the Dolphin, like I said, was an eye-opening experience. Chuck had a very big ego, and I don't think he was always careful on some things. He wouldn't always do a static timing analysis. The technology of the boards was called Stitchwell technology, adopted apparently from satellite and spacecraft program, where a big machine, you could take a board and it would directly place 2 wires between 2 pins and weld them on both ends. So the amazing part is you could spin the board just in a few hours. If you had a change to the net list, you could submit it to, I can't remember her name, the woman who Rosemary, who ran the Stitchwell machine, and you get this new board back. And so I'm not sure it didn't encourage simulation or thinking about it very well, but you could very rapidly turn around the board, and we probably went through many iterations of boards before you commit them to etch to our printed circuit board later. But one of the problems with Stitchweld is maybe the welds wouldn't always be good. I'll never forget having a Dolphin board out on a card extender, and I had to twist the board to get it to work. That was not a good sign.
Yeah, it was very good to rapidly prototype, but it was not reliable. So
and I think there were timing issues in it as well. But anyways, it also was the Dolphin was very expensive, and it was kind of built for multiprocessor perhaps with a very capable memory system. One problem it inherited from the Alto was that the microcode would decide when to give up control. So you could take control of the CPU as long as you wanted. And Chuck and I had a constant battle going on where I'd come in the morning and the cursor would stop working because I was doing the cursor microcode for him. And I would say, Chuck, I'm losing cycles to the your disk microcode. So Chuck would grumble and go fix his disk microcode, and my cursor would work. But the next day, my cursor would stop working so we had this constant battle of who would get, enough CPU cycles to get work done, and there was no way to allocate the bandwidth among all the users. It was just a free-for-all. It was based on priority, so a bit like normal I/O buses, and so it just didn't work. And so it was a painful lesson. Chuck, it was the interface. He had to fly down to El Segundo all the time. The old scientific data systems people had been converted over to help bring our products to market and productize them. So one question is, was there any serious consideration to productize Dolphin? And yes, there was. Yeah,
is that why he was working with the El Segundo people?
Yeah, he was going down there. It was on the track to be productized, but the decision was just made that it was too expensive. It seemed to have timing problems. It was just a second system syndrome, and so it was a very tough decision that someone made to cancel it. And then at the same time, Butler Lamson and Roy Levin came up with a paper design which addressed the fundamental issue of the two previous designs by having a fixed schedule to access to memory in the microcode. So it was called a round, and there were 5 clicks in a round. I/O devices would get 1 slot or 2 slots. So they would always know when their microcode was running that they would get another access within a certain number of microseconds to main memory. So as long as the system met its cycle time, I/O was guaranteed to work, which is a remarkable aspect of the Dandelion. It was called Dandelion. That was the name of the machine.
Well, so I remember it was called Wildflower in the paper design, right. But that really was the impetus to start Dandelion. So,
yes.
So maybe we should. So that was your next work, was on the Dandelion system,
yes.
And that, of course, was I used the word seminal system. It was it changed the world. That one. So maybe you could tell us a little bit about, what was Dandelion all about? You started talking about the architecture that was really so ahead of its time, and then you started working on it.
Yes. Yeah. So. I went back and looked at my notes. It was interesting, actually. Myself and Bob Belleville, who was my manager at the time, we were both initially skeptical of actually using the Alto Dolphin and Wildflower methodology for a product, because we had seen the bad track record of the Dolphin. I actually wrote this big memo. It's just like the dinosaur era. But eventually I came around to the fact that the Wildflower had this feature that if we met the cycle time goal, it would be guaranteed to work. And it was a very synchronous machine. It was almost like an appliance built for the set of I/O devices it had. It was so synchronous that 7 display bit periods, each one were like 19.6 nanoseconds, equaled 1 CPU clock cycle, 137 nanoseconds. And by the way, 137 is my favorite number. That's the fine structure constant from physics. So I always thought that was cool. 137.14, very close to the fine structure constant. And there were 12 display periods per disk bit. And 3 clock cycles per memory access. So the entire core of the machine was synchronous. Now the Ethernet was at 10 megahertz and it was asynchronous, so it needed a FIFO and a synchronizer, but the entire machine was synchronous. So we had to meet the cycle time goal, or the machine would work. Right. But if we did, all the I/O was guaranteed.
It was guaranteed.
Now the I/O processor, which you worked on, was also asynchronous, but doing the low-speed I/O.
But that was a whole separate processor, and then of course you had an interface.
Well, and you used an 8085?
Yeah.
It's kind of ironic that the germ of the demise of Xerox's D machines lay in the Intel 8085 in the bowels of the Dandelion.
I mean, the I/O processor was kind of like a PC, right?
Yeah.
That we had a little after that.
It was. Yeah. And it ended up eating the whole rest of the market alive a few years later. So there was this round-robin scheme, and 2 slots were dedicated to the Ethernet, 1 slot for the disk, 1 slot for the display, 1 slot for slow-speed I/O, your stuff. And then anything that wasn't running ran the emulator, the Mesa emulator. But Mesa Okay. So I was responsible for the CPU card design, which was based on 29 of the 4-bit 2901-bit slice. We had a 48-bit microcoded word. When I was also responsible for the Ethernet design, and at this time, because we were shorter on real estate, I decided to go against Boggs' advice and do a half duplex. Since the wire was half duplex, it was only sending and receiving at one time. Why not make the controller be half duplex? So receiving would have priority over sending. Bob wasn't too keen about that, but it ended up working. Ron Crane designed the analog phase lock loop part of it. And Ron also designed the display. He even had a clever mechanism for doing smooth scrolling, which wasn't adopted by the software people. And he did the Ethernet cabling, as we said, and Ethernet transceivers, and fixed them after they got hit by lightning, all those stories. Dan Davies did the disk controller. Roy, you did the low-speed I/O based on 8885. My friend and mathematician Don Charnley did BitBlit, the microcode that moves a rectangular area in memory to another rectangular area, and the microcode assembler, which is called MAS. He also, I wanted to do an arbitrary 16-to-1 rotation, because you needed that kind of thing for the moving things in memory. And he suggested do an arbitrary 4-bit rotation, then you could follow it by 2 1-bit rotations to get an arbitrary. So you could do an arbitrary 16-bit rotation in 3 instructions. That was kind of a neat suggestion on his part. And other people did various microcode, Jim Frandine, Amy Fashnot, and Jim Salmon. Also at that time, they asked me to become owner of the Mesa. Mesa was the proprietary language that had been developed. Instruction set architecture document, which had been modeled after the IBM PrintSops document, which I didn't realize at the time. But that taught me about the rigor of having to define an instruction set. Very precise definitions. I started writing them in Gordon Bell's ISP notation, and they asked me later to convert it over to Mesa code, because then they would take the Mesa code description of the opcodes and just run them on a simulator. So that was a better way to test to make sure the opcodes were defined correctly.
Do you remember how it ended up that you were given ownership of that, because you were someone in the hardware team?
Yeah.
And they chose you?
Yeah, I don't remember. No,
very appropriate, I think, but
yeah, I
just
thought it was
the
pretty
fact
cool.
that they did that was is kind of unusual.
Well, I guess I was responsible for the microcode for the Mesa emulator. So in that sense,
perhaps that's why
it made
yes.
sense for me to do both.
Right.
Now, one thing that I noticed at the time was that what I call the Mesa High Priests, I can supply names later, is a classic what Dave Patterson later called CISC machine, because every week they would redesign the opcodes to make the static code size smaller based on compiling some programs, because it had to fit in a small amount of memory. We only had, we weren't sure whether we were going to have 384K max or like 128K max, and that's not very much main memory, 16-bit memory. And so they were rejiggering the instruction set every week to make it smaller for code size, also to leave things on the stack, maybe that next instructions could, further down the stack, next instructions could use. Very CISC approach. And, everyone was kind of doing that at times, so no one thought anything about it.
And later on we'll talk about CISC versus RISC.
Yes.
Can you talk a little bit about the bring-up process for Dandelion, because there's a lot of innovations there as well.
Yeah, so we had no experience in this, but I thought, wouldn't it be cool to have all 5 boards be accessible simultaneously? So I proposed what was called a windmill, which was a central structure with a flexible backplane around all 5. You plug the boards in like petals of a flower. Wildflower, windmill. Yeah. My background in natural history, maybe it all made sense. That was the same kind of way that crays were designed. And I learned later that the IBM 801 RISC computer prototype was designed exactly the same way. All the boards were around a vertical column, and you could squish them together or open them up. So that way we could examine signals simultaneously on boards without having to put them on card extenders.
Now remember, Cray's production machines are like that too.
Yes, the Cray ones were.
For access later.
Yeah, He had trouble with card extenders too.
Yeah.
But the funny part though is these cards were stitch weld, and the characteristic impedance of stitch weld lines is higher than on a printed circuit board. So we were taking somewhat of a gamble in designing in stitch weld first, which is faster than printed circuit boards. And I was kind of aware of that, which also led me to be more conservative in the timing, because I knew when we switched to PCBs with a lower characteristic impedance, like 50 ohms instead of 100 ohms, the signals would even be slower and more crosstalk. But it was a risk, but it seemed like it worked.
Right, and then we had a debugging system connected to an Alto.
Oh yeah, so that was so cool. So we used the previous computer to debug your current one. So Pitts Jarvis developed this thing called Burdock, which is a beautiful user interface where you could set breakpoints, you could run microcode, you could look at registers. There was an umbilical cord, we called it, that went over to the Wildflower. Did that go through the IOP, I think? I don't remember. Did it go through your thing?
Yes, it did, actually.
Okay.
Yes.
Yeah.
By the way, do you remember why it was called Burdock?
No.
Well, there's an English drink called Burdocks and Dandelion.
Ah.
So, and there was an English researcher who was working with us, Dick Snow.
Ah, okay.
And he came up with the name Burdock. So anyway, that's a little piece of trivia.
Oh, that was a beautiful program. It's too bad something that couldn't be commercialized. So I did you could have multiple microcode machines, you could have multiple sources going to multiple destinations, and so I did a static timing analysis of all of them, and some of them just didn't work. So it was kind of ugly, so we had the assembler, MAS, disallow those operations. So there was a big chart that showed what could be sent to what and what was illegal. Ugly, but I think that's what helped us get it to work. So I was kind of proud that it was working, coming up in the lab. And I remember one day we invited the product engineering people from El Segundo up into the lab and introduced them to the board. And the board was sitting there, and I was so proud of the diagnostic program I had written. I said, well, let's pull out a random chip from the board and see what happens. Boy, what a learning experience that was. So I walk up to the board, I take, the little chip, TTL chip remover, and I pull out a chip. The diagnostic is still running. And I kind of looked at it like, I think I missed something. and I scratched my head and looked at it later, and I'd written the diagnostic, not being new to diagnostics, you'd say you would put the expected answer in a register, and then you would compute the answer, then you'd compare them. Well, the expected answer would go through a driver to a thing called the X bus, and I removed, the driver. But when the new answer didn't get put on the bus, but the expected answer, which had been put on earlier, there was so much capacitance on the X bus that it actually hung on for an entire cycle for 300 nanoseconds. And so even though I pulled out the driver for the new answer, the correct answer that had been put there was still capacitively sitting on the bus. So I learned that in diagnostic programs, you should never nearby what you're expecting put the right answer, because it might hang around for some unforeseen reason. That was.
So another question. So the MESA development, you started getting to PrintSops. Maybe we could talk about that more. Oh. But the MESA work had been done for many, many years, independent of Dandelion. There must have been some other tools that had to be developed for Dandelion, like Burdock was one, but what about the microcode controller, microcode compiler? So do you remember who did those tools?
Well, the microcode assembler, you mean?
Sorry, assembler.
That was Don Charnley.
That was Don Charnley.
Yeah, Don Charnley did a microcode assembler.
Yes.
The MESA compilers and all that. I don't remember the names.
Yeah.
We'll have to do that in a whole history. We should the museum should do a whole history on the Xerox STAR. One thing I remember when I started, when we made I almost forgot to talk about. We made this transition from the paper Wildflower to the actual design. I would question Butler. I would say, Butler, why don't you work on it? Or Roy, and they kind of took this approach. Well, it's easier to design it on paper than to actually get it to work. And he had a famous quote where he said, "The trouble with paper designs is you don't get bloody enough." So I always thought that's interesting. It's time to get bloody, So okay.
So let's see. So maybe a little bit about how long it took to develop the Dandelion.
So I thought we did it pretty quickly. We started the design, according to my notes here, in mid-1978. So a little less than a year after I joined. So the whole experience with the Dolphin got over pretty quickly. The first CPU was stitched weld in July a year later, running diagnostics a month later. The display operational December 1979. The first MESA program ran in March 1980. Ethernet. Then I started to work on the Ethernet. So I did the CPU, then the Ethernet in series. And that was the same time we were doing the spec. We transmitted the packets to a Dolphin in August of 1980, just 8 months later. Committed the board to etch in September. And at that very time, Digital Equipment, Intel, and Xerox announced the spec for Ethernet, the DICS, as it was called. Gordon Bell from DEC, I can't remember who it was from Intel, and Bob Metcalfe. Bob realized that Xerox would keep everything proprietary. That was the thing you did back then. You did not, you kept your golden jewels private. Remember all that? Yeah. We were a very secret project. Everything was proprietary and quiet, secret, and non-open. But Bob somehow convinced, I don't know how he did it, that's for his oral history, I hope he's done it, the lawyers to open up the Ethernet spec.
Right, because that was against the philosophy at the time.
He was totally against the philosophy. But for us, what was fun about it is Ron Crane was actually writing the low-level spec. Remember, he did it in STAR, actually. It was a STAR document. And I remember, and I've checked with Ron, the only thing that was changed from Ron's spec and our work was the bit ordering and the byte ordering, big endian to little endian or vice versa. And also the CRC was improved. But those were the only changes made between the, so we kind of felt like, hey, we've got the Ethernet controller going to market at the same time the spec is going public, so we had an advantage, time to market advantage. So we didn't care that it was going open either. No.
Yeah, and that happened after the announcement of STAR, the formal spec.
Well, no, my dates show that it happened in the same month. So in September 1980, the DICS spec was signed.
Oh, that was actually earlier because STAR was announced in 81.
81. It was actually earlier.
So it was earlier.
Yeah. One thing I remember working with Hal Murray he did the device driver for the Ethernet. I did the microcode, he did the device driver. So we had to battle, whose bug is this, in endless nights. Working there at Xerox was like at a startup. I mean, we worked past midnight. I used to go home typically at 2 or 3 a.m., ride my bike by the graveyard in Los Altos, which is kind of spooky. I would wait till 11 o'clock at night to call my girlfriend, who had temporarily moved to Bakersfield, to save money for the bills, which you probably got. But it was truly a startup environment. And I think back about it, and some of the things I didn't mention earlier, all my outdoor trips when I was younger, I did solo backpacking trips when I was in high school to the Chiricahua Mountains. The cabin my father had built south of Mormon Lake by Flagstaff, I'd go out wandering around by myself all day or sleeping at night with coyotes around me. And so I had a very strong sense of individual strength and fortitude, and things didn't scare me. And so I could stay up all night by myself if I needed to, working on the schematics and driving by graveyards at 3 a.m. And so I think that was kind of the confidence you get in solo backpacking. Truly, in high school, I was doing solo backpacking. Really made hanging around at a workplace late at night pretty easy.
Yes.
So
let's see. So the STAR. Sorry, did you have a thought?
Well, I was going to say when it was announced. Yeah.
Yeah.
So again, we worked with the SDS crew in El Segundo to productize it. They did really all that work. The hardware was first announced in November 1980 as the Information Network System that we now know, or INS 8000. So they actually first announced a storage server, or they called a file server, a communication server, and a print server at the end of 1980. The hardware was barely working at that time, but they announced them anyways, which was a very bold step. And then they announced the Xerox STAR 8010 Professional Workstation in April 1981 at the World Trade Center. We weren't there. Charles Irby, I think, was there. A professional information system, a personal information system for business professionals whose main job is to create, interpret, and manage information and distribute the results. So email, printing, all the things that people waste their time on today.
Yeah, I remember that the innovation of this whole idea of servers was a new thing, a client-server paradigm, and that was, to their credit, something new that came up.
Yeah, that's a good point. That came there, right there.
That came right there, because in the beginning, everything was the workstation, and no one thought about the servers that you need.
Yep.
But
yep.
then...
Well, that then made it expensive too, unfortunately.
Yeah, it was expensive.
But so that it was announced with a almost $17,000 purchase price, which would be $50,000 today for, a 1 MIP workstation. But it moved things quickly on the screen. Or $700 per month rental, which is $2,000 per month today. It was also shown at the National Computer Conference, NCC, in May of that year, and that's where Steve Jobs checked it out, apparently. He was there to see what Xerox had brought to the market. Oh, and you're right. The DIX Ethernet announcement then happened in May of
okay, but it was concurrent.
yeah.
So, of course, the STAR was a phenomenal technological success, but not a business success.
Well, first of all, it was
Xerox.
a huge investment. I mean, there were hundreds of people on the STAR project, right? Probably 200 total, maybe, on the software and the operating system.
Probably three-quarters of them were software.
Were software people, yeah. So, to bring to market all of that. Yeah, so way ahead of its time. I mean, so at $50,000 in today's currency for a single workstation, professionals said, okay, I don't know how to type.
I don't want to type.
I don't want to type. Yeah, I have secretaries, called secretaries who type for me at that time. You're telling me you want me to purchase in today's dollars a $50,000 workstation to make my secretary more efficient? Oh, and then you want me to purchase a file server, a print server, and a network box as well. So the total cost is going to run to like $200K, which would be like almost $1 million today. $1 million today, just to make my secretaries more efficient.
So you think those are the kind of reasons that, because, so if it had been 10 times cheaper, it might have been different
yes,
then.
It would have been totally different. And what's this thing called a mouse? And actually, when I went back and looked at the original product release, the original press release called it, quote, an unusual control device, because a mouse had never been announced to the public before.
So I think you're right. Ahead of its time is the right description for the problem.
Yes. And later I learned maybe only 20,000 were sold on, that's what Dave Liddell has said, the number, but the major customers I saw and heard of were NSA, a visit I had the NSA later. Radio Free Europe used them because they were multilingual, and they were very popular in Japan. They were the first Japanese kanji workstation.
Yeah, so I remember that the Japanese were very interested in it because this was a way to produce their very complicated script in an easy way.
And a system that cost quite a bit less,
Yeah.
And it was very reliable. We never had heard of any field issues on hardware. Software was very reliable, even though it had a very basic virtual memory system. And in November 1981, the Xerox STAR received the Fortune Magazine's Product of the Year award, which was kind of cool. They every year they select what are the coolest products that year in the United States and the world. So, unfortunately, right after it was announced, just 4 months later, IBM announced this thing called the PC. 4.8 megahertz, 8088. It was announced 4 months later, and everyone thought that the rug had just been jerked out from under them. And Microsoft and Bill Gates were putting the world back 3 decades, because here the STAR user interface had been designed to be very intuitive, easy to use. They had psychologists and sociologists. It made sense. You started with an existing document and modified it. You didn't have these horrible DOS-like command interfaces, and STAR didn't feature spreadsheets very strongly until later. So it was all kind of downhill from there. I mean, the emphasis shifted from Xerox PARC to Apple at that point. I remember the day that Steve Jobs came by and visited PARC. Larry Tesler, who knew my girlfriend at the time well, who gave the demo, he moved to Apple. It's all known history. Bob Belleville moved to Apple and managed the Macintosh program. He'd been gunning while in STD. Remember, he built this little tiny, what do you call it? Cub. A little tiny 6800 based or something? It was an Intel based.
Well, I think at that point Intel had come out with the 16-bit processors, and he wanted to play with them. And so Cub was based on that.
Yeah, so he kind of knew that the high priests and the Xerox doing their own language that needed a microcoded machine and operating systems was not going to make it. So he went to Apple and actually managed the Macintosh program at Apple, on which my friend Mike Boych worked, who I'd run for freshman class president against in high school.
That's right, yeah. So then you actually, before you left, you were still at Xerox. You moved to PARC per se.
Yeah. Well, right before I left, I remember there was one interesting thing that happened. This guy named Forrest Basket, I don't know if you remember that, was coming around, and he had been into computer benchmarking. He benchmarked craze and stuff and really understood it. He had this little program called Puzzle, which just did some kind of puzzle in software, which he was running on all computers he could find. And he ran it on the Dandelion, and the performance was really bad.
Bad. Okay.
It was really bad. And I've tried to find what the results were, but even though we had a 7 megahertz clock, it took 3 microcycles to do in memory. So it was we were less than a 1-MIP machine. So, here we were taking what could be a 7-MIP machine and making it into less than a 1-MIP machine. So that really got my attention. Why had we done this? So, and then, but I always wanted to work at PARC proper since we had been there so much. And so in 1980, I joined PARC itself, and I joined Lynn Conway's team, who was doing.
So you actually moved over before STAR was announced, then it sounds like.
Oh no, I'm sorry, 82. 1982 is
okay.
when I have that wrong. Yeah, 1982 is when I moved over after the STAR announcement. Yeah, sorry.
So you joined Lynn Conway's group.
Yeah. So Lynn was doing VLSI design.
Which is a completely different type of work from what you were doing before.
Entirely. She was a very kind and good-natured person. I never saw her angry. She really cared about people. She really engendered the best in people. She was really an educator, with her VLSI design methodology. Her whole history is there, how she created that whole program to get students tuned in to chip design. I started working with Dick Lyon. He had done an innovative design for an optical mouse based on cross-coupled neurons. It would you could work on blue jeans or any pattern that had equal distance spots. It would stabilize on a pattern, asynchronously stabilize at another one, and if it detected a motion of the dots, it knew which way it had moved. Very brilliant design, and I helped productize that for the product group. And I worked on some other things. I actually did do a DARPA MOSIS chip using Lynn's and Doug Fairburn's Icarus program. Other people did some more interesting chips, but it got my fingers into chip design. I saw it, though, as needing a lot more software tools. It just wasn't possible to really design an interesting chip by hand. I mean, Lynn kind of promoted the idea. In jest, one could say all you needed was a blue, green, and yellow crayon to do a chip, because these wires, when they cross, would give you a transistor, blue would give you metal, but there weren't design methodologies in place. John Osterhout was just formulating his IC layout tools, which would really be needed. But that's research. That's the nature of research. Right. Lynn.
And then you also worked on the PARC Dragon work, which is kind of prescient for the future.
So
we'll get to that later.
Yeah, so while I was realizing that the tools really weren't in place to do interesting chips, there was an attempt to do an interesting chip program at PARC, and it was called the Dragon multiprocessor. It was a whole new idea on how to design a microprocessor, really careful attention to the cache coherency protocols. It was based on a split transaction bus, packet-based, or you could send a request, later get the result back, so you wouldn't tie up the bus for a long period of time. Very carefully thought out cache coherency algorithms. Jean-Marc Freilong and Pradeep Sindhu were the lead architects, and Chuck Thacker asked if I would work on the I/O chip for it, which I agreed to start speccing at least. But right about that time, PARC imploded, or I guess maybe exploded would be a better word. For whatever reason, it's all been written up. George Paik kind of came down from his nest on the first floor and poked at Bob Taylor's tight-knit cult leadership, and people loved working for Bob Taylor, and so Bob resigned in protest. They were trying to get him to do more practical work, maybe they thought he had too much power. I don't know. But everyone went with him in CSL, Computer Science Lab at PARC. And Butler Lamson did, Chuck Thacker. They went to formed the new Systems Research Center, SRC, at DEC in downtown Palo Alto.
Digital Equipment Corporation?
Yeah. So I was standing around all these empty offices one day with Dave Patterson, who had been consulting to the Smalltalk group, Alan Kay's Smalltalk group for some time, and he knew me based on my reputation for designing the Xerox, the Dandelion hardware. And he asked if I might join he and his student from Berkeley, Bill Joy, at a startup doing 68,000 base workstations, but also planning to do a RISC-based design. And I kind of looked at him like, 68,000 base workstation company? There are lots of those out there. Why is this one going to be any better than all the other, dirtball companies? And but he was consulting to Bill and the people at Sun, who were about a year and a half old at that point. And I just ignored him because I was at PARC, and I spent some time doing a hand design for a Mesa processor. I don't know how practical it was, but it seemed like somebody had to get going on it because there really needed to be a full chip Mesa chip implementation. Later SSD did that themselves, but then fortuitously this is early '94. My girlfriend Robin Bearsford asked me to go pick up an album at Tower Records.
Okay. 84.
Yeah, 84 on San Antonio Road. And when I went in there was to pick up the album. There was Bill Joy and Eric Schmidt, who had joined Sun a few months earlier, walking up and down the aisles talking about work. You never stop thinking about work at Sun. And they saw me, and they had contacted me before, and they twisted my arm and they said, "Why don't you come work here?" And so I agreed. And so my wife hadn't sent me to Tower Records that night.
Serendipitous things.
Yeah, I don't know what my future life would have been. My interview with Andy Bechtolsheim was odd because it consisted of him telling me how he had developed a new static timing analysis tool, which was a spreadsheet. And I didn't realize at the time he had a bad reputation for also ignoring timing issues. The Sun 2 design had manufacturing challenges. In fact, my first day at Sun, or maybe during the interview, one couldn't help but to notice in one corner of the half-empty building, there was the CEO Scott McNeely, Bill Joy, and Andy Bechtolsheim, and Vinod Khosla plugging and unplugging 6810s until they could find one that worked, because there were timing problems in the board. That was quite an eye-opener. And Vinod Khosla gave me my offer, and he said, "Do you ever want to be able to afford a house in Silicon Valley?" That was the criteria for working there.
Right. So let's see. So that's 1984, and so
Yep.
you decided to leave Xerox and move
Yep.
to this new little startup called Sun Microsystems.
And
So what was your impressions when you got there?
well, also, before I forget, that was the year I married Robin, too.
Oh, okay.
So it was a
very busy year.
busy year, 1984. Well, yeah, so Sun was a very small company. We were just in one building, but the very first day, I was kind of jolted into realizing maybe I hadn't moved that far, because in the mail room were printouts, Dover laser printer printouts from Stanford that people were driving to Stanford twice a day to pick up. And our people at Sun were using the Alto network.
Right, Dover was a Xerox printer.
Yeah, it was the Xerox printer. Yeah, Xerox had installed at Stanford a large number, kind of granted to them, a large number of Altos and a Dover laser printer. That's how Andy Bechtolsheim got his motivation to do a different job, do an open workstation instead of a proprietary workstation from seeing the Alto. But people at Sun were actually using it. And I thought I was still at Xerox because the little sheets were in the inboxes. So really amazing people at Sun. So Bill Joy was a remarkable visionary individual, just brilliant. He's a visionary of the highest order, and he's also a grand weaver of tales and perception. He did what I would call cranial acupuncture. He could walk into anyone's office, software, hardware, whatever, and within 30 seconds, totally understand what they were doing and already be giving advice. And he'd walk out of the office and the person would go, "What just hit me?" And he also had this technique of speaking so rapidly that as you tried to process it and keep up with him, you'd start falling behind. And eventually he would just flummox you. You'd be wordless. It was one of his classic debating techniques. And you know, Dave Patterson had remarked he would speak more than he would in class. You know, he was just a very on the other hand, Bill could also be extremely pragmatic. I mean, you know, it's like he was a binary personality. Here he'd be crazy and visionary, and a few moments later he'd be practical and let's just do this, you know, to get it done. Dave Patterson was the consultant. Dave had a very fatherly figure, very strong, generous, equanimous, pragmatic. You know, he was really good at bringing people together, tying ideas together, because he did that, you know, at Berkeley a lot. He wasn't afraid of conflict or arguments or fights. And later I learned he was a wrestler in college, which kind of explained why he wasn't afraid of fights. But he would help break up the arguments, the catfights we would have all the time at Sun. He would kind of say, that might be the way how you think about it, but I think this is the way it's going to be. He was very pragmatic in getting people to see the light. Andy Bechtolsheim was brilliantly meticulous and extremely detail-oriented, and he would get ornery. He would only build things that he knew could be built right then and at low cost and to market quickly. He didn't really look out 2 or 3 years. It was only next year. People used to characterize him as making a Porsche out of Volkswagen parts. He's the only person I knew of who could actually have 2 thought trains going concurrently. You could actually talk to him about 2 things and he wouldn't trip up. Just an amazing capability. And he's a super optimizer. He always kept himself in the lab. In fact, you know, he really drove a lot of people nuts years later when he became known to be extremely wealthy from all his holdings, but he'd still be in the lab doing an engineer's work. He never kind of backed away from that. Scott McNeely was bitingly and hilariously funny. Jocular, cutting humor. You know, he had a lot of fun being the rabble-rouser in the industry. He didn't understand computing at all, but he totally trusted Bill and Andy. Totally trusted them, which was a great relationship. I'll never forget, in my office on the 2nd floor, every Friday he had a beer bus. The beer bus was right outside my office by coincidence, and he would give away all the freebies that had been given to him that week by executives at our company. He'd just give them away to all the employees so he wouldn't be influenced by them. Bernie LaCrue came on later, was the senior VP of engineering, a very respected and passionate and caring person. We also called him Little Napoleon because he was very detailed, driven and forceful. You know.
So how big was Sun about at that time? I mean,
well, I was employee 278. I don't know if you can see that in the badge or not. I was one of the earliest hardware engineers there, among, you know, certainly within the top 5. Sun had no marketing or salespeople. It was all mainly engineering.
So a few hundred people, it sounds like.
Yeah, a few hundred people. It was 2 years old. I started on March 1st, 1984. So speaking of that, during one of the early beer bus, Eric Schmidt drew the entire org chart of engineering on one piece of paper. So that showed you how small the company was. There's Bill Joy, Bernie, Andy. Eric Schmidt was head of all the software guys. It was amazing. We were a full function company at that time. There was a compiler group headed by Steve Munchnick. There was a Windows group, Jerry Farewell and other people. So we already had a GUI group and a graphics group, Jerry Evans and other people. There was a systems group. We already had a large OS group, Bob and Tom Lyon. Bill Shannon, Dave Goldberg, John Gilmore, who later went to Linux. There was a documentation group. There were hardware groups. So it was a CAD group environment. I mean, it was a complete system structure. So to walk into that and say, let's do a new RISC processor, a lot of the pieces, a lot of expertise was in the company. It's not like we had to go searching outside the company for other expertise.
But on the other hand, you told me that you thought you'd gone a step back when you went there because
so
the WYSIWYG, and then you were Unix now with this.
Yeah, all of a sudden you show
line.
up with this command line interface. It looks like a lot like a DEC command line interface. Command switches, a whole bunch of switches, and and more switches, and what happened to the WYSIWYG world? There was no visual. Bill Joy had a program called VI, Visual Editor, but it was modal, and it was like Tico, the DEC's Tico editor. You had to individually change characters, and so I was like, man, this is a startup company based on this. But luckily, FrameMaker developed a STAR-like application that ran under Unix and on the Sun the very next year, and it looked just like the STAR interface, called FrameMaker. So that made us feel a little bit better.
And they had Ethernet too on their machines.
Yes, well, Andy really believed in the Ethernet. I mean, he strongly believed in the whole PARC vision, bitmap graphics, Ethernet. That's what really helped drive Sun. The network is the computer, strong network performance. So my very first day at Sun, or first week with Bill Joy, I'd gone there on the expectation that we'd be designing a RISC machine. Well, Bill kind of surprised me by saying, well, that's not really what the plan is at the moment. Bernie LaCrue, his vision was the bread and butter, the next bread and butter of Sun would be a Motorola 68020 based system with one or two RISC coprocessors, on the side. And so Bill and I thought about, debated, I can see in my notebook a lot of schemes of, maybe you would have an 020 and a RISC, and they would multiplex memory, so they could share the same cache. Basically, Sun was last in floating point performance on Don Guerra's LinPack benchmark. They had a floating point accelerator card they were developing, but based on the 68,000 stuff, it was horrible. So Bernie said, let's design a floating point coprocessor. And Bill said, well, it should be based on RISC then. Well, I told Bill I did not come to Sun just to design SPARC as a coprocessor. And I was adamant and
RISC coprocessor.
Yeah, I did not come there to design it as a coprocessor, to something else. I came there to design it as the main processor. And Dave Patterson kind of felt the same way. Another person who felt the same way was, I learned was Dave Goldberg, who had been at DEC. And he said there's no need for a 68020 anywhere, and every product shouldn't try to do everything. But we spent 6 months getting Bill and Bernie, I guess, to change to the idea of making it a main processor. So the way we pulled that off is, in design at the time when I arrived, was a 68020 based board that Bill Van Loo and John Watkins were doing. 68020, cache, memory system. So we said, we'll just design a plug-in replacement for that board. Same backplane, same memory, same everything, and that way if RISC falters for some reason, we still have a product. And so that got the go-ahead. The FCS goal, first customer ship goal, was changed from mid-85 to mid-86 at that point, and we started working on it.
So at that point, what was thought would be used for the RISC processor? I know we're going to get into a big story about SPARC.
Well, we had no idea.
It wasn't then yet.
Yeah, we had no idea. So I was the group lead for defining the RISC architecture. Dave Patterson was the consultant, so obviously the RISC 1 and RISC 2 by then maybe designed at Berkeley was well known. Catavanus' thesis was published. But I said, okay, let's look at what we know about all the RISC machines. So I looked at what we knew about the 801, IBM 801, John Cox machine from IBM, from the paper. and a little bit of inside information. The Berkeley RISC won, obviously. DEC had a design called Titan at the Western Research Lab that Dave Goldberg knew about. The Acorn people had their ARM stuff out there. Fairchild was doing work. HP was doing what was called Spectrum, later called Precision. We knew a little bit about that. Ruby Lee was the architect, and she was the husband of Howard Lee, who was my manager soon there. So there was a little bit of, they were very tight though. Steve Munchik wouldn't share anything about what they were doing. Pyramid was doing a RISC machine, and George Taylor had been involved. So I kind of looked at all these, and they were all pretty similar. So I said, well, hell, let's just mainly stick with instead of inventing something new, let's mainly stick with the Berkeley RISC one. It's in the public domain, so we won't get sued. And they've addressed a lot of problems, so let's mainly follow it. I mean, we can make some changes. We needed to add floating point, primarily. I initially thought of just some dumb coprocessor interface to the Waytech floating point chips, but Bill set me straight that really needed to be a proper instruction set.
But the idea still was to design your own processor.
Yes. Yeah.
A custom processor.
And we didn't know how. We had no, so we started, technology firms, we started calling technology firms to see how we're going to do it. I knew the Xerox approach wasn't going to work. John Doerr, who had started Sun as a VC, had started Silicon Compilers, and I would visit Silicon Compilers and go, this stuff isn't going to fly. We're not going to be able to build a fast enough cycle time. The right register technologies in there, you really needed master-slave, solid flip-flops, and not these kind of flaky CMOS charged devices. And so the companies that we talked to, I looked at my list, were CTI, CMOS Technology, BRI, Barvon Research, LSI, still exists, WSI, Wafer Scale Integration, how's that for an acronym suit? Cypress, TI, Texas Instruments, Alphatron, Toshiba, and then Fujitsu. So we looked at 10 possible things, and they were all standard cell based. And it was not a very good feeling, like, how are we going to pull this off? There's only like 3 of us. But luckily, we hired Anat Agrawal from STC, Storage Technology Corporation, who had also, they were trying to build an IBM compatible machine, and they were familiar with Fujitsu's gate array. So right about then, Fujitsu announced a 20,000 gate array. And we looked at each other and we said, 20,000 gates? I think we could do a RISC in 20,000 gates. So we went with Fujitsu. 20,000 gates, but also a quarter of the gate array could be SRAM. And I have a picture of it. So a gate array. So we did the RISC integer unit in 20,000 gates with a quarter of the die register file. For the Windows, obviously, for the Berkeley's register windows.
So the idea was to use a standard cell.
Well, the gate array.
Gate array,
no,
actually,
that was gate array.
but not full custom.
Not full custom. And Fujitsu did not have the greatest tools. The team, I wasn't part of the chip design team, Anat and Masood Namju and Don Jackson on Floating Point did that, but we used DAISY workstations. Vinod Khosla had been at DAISY before, so we used that as a schematic editor. Didn't have good timing tools. The net lists would be generated on magnetic tape, flown to Japan, where they would run on a mainframe to do the place and route and timing. So it was kind of a long separation between schematic and timing. Yeah, it made it very difficult. But anyways, before I jump ahead, there was one really big event in April 1984 that got our attention. So we knew that IBM had the 801. Everyone knew they were doing various successor projects based on it. In fact, I later learned when I went to IBM to work there that my first manager, Richard Freitas, actually worked with John Koch on the 801, designed the I/O board. And after that, he actually designed an 801, worked on an 801 system as a coprocessor to the IBM PC. So at the very time that I said, no, we're not going to do it as a coprocessor, inside IBM, they were doing it as a coprocessor. But anyways, we knew that IBM was doing something, but we didn't know what. And in April 1984, we heard that IBM was going to announce their RISC work at Stanford's EE, what is it, 380, 392 seminar. So anybody who was, everyone who was anybody on RISC design was in that room. Hennessy, the MIPS guys who hadn't started yet, we were there, and we were all holding our breath. What is IBM going to announce? Because we knew if they got it right, we were doomed. Well, they got it wrong. They announced a chip called ROMP, and it was a chipset really designed for typewriters. No cache. It had direct access to main memory, 5-cycle load and stores and take and branches, 5 cycles. It was as bad as a CISC machine. So the cycles per instruction averaged around 3. It was pathetic. So everyone just breathed this huge sigh of relief. MIPS was probably started that day. We went back and goes, holy shit, they blew it. We have a chance. So, we said, let's go. And
so that really started the whole SPARC track. I mean, I know SPARC's name came later.
Yeah. So
maybe we could move on to that whole story there.
Okay. So we knew we had the Berkeley design to leverage off of, but we knew we needed to make changes. We needed an MMU, we needed a floating point, we needed to tweak it. So I established what I called the SPARC Architecture Committee. So
which probably wasn't called SPARC actually. Then,
no,
right?
it soon was. The way we came up with the name SPARC was one of the guys on the team who wrote Simulator, the instruction set simulator, Will Brown. We just took 5 buzzwords, and he wrote a program that printed out all 5 factorial combinations of them, and one of them was Sun's Processor Architecture for RISC Computing, or SPARC. So that's how we got the name, Sun's Processor Architecture for RISC Computing. So anyways, we had this committee, and I led the committee, and the idea was to get lots of input from the compiler people, the OS people, make it not a slow thing, but to get everyone's input to design a decent instruction set. Designing an instruction set is like designing a house. You want to have the rooms in the right place. They all want to be functional. You don't want doors to nowhere, but everyone wants to put the kitchen sink in every room. Everyone wants everything because they know the egos get involved. And Dave Patterson really helped tone down the egos. We met on a regular basis. I was also the owner of the SPARC architecture manual, so I had control of what was written every week. And in fact, the version numbers of SPARC were just the version numbers of my document, 1, 2, 3, 4, 5, 6, 7. 7 was announced. The 0.1, 0.2 thing I thought was silly. There are integers, so let's just count. So some of the innovations that came from the guys were simple, but things like Richard Tuck and the compiler group said, let's break apart the call instruction from register window changing so that you don't have to move the register window pointer if you don't want to, and therefore you can do things like recursion better. You can do, you can actually not even use the register windows if you want to, so that was a good idea. The compiler folks insisted on sign extension, load byte sign, and things like the DEC alpha architecture did not do that, and that was an impediment. People really wanted, the C language really wanted the C sign extension. And we were worried that might affect the cycle time, so it was not a simple decision. We were that low level. I felt that in terms of the MMU, at Xerox in the STAR, we had the MMU in main memory. I mean, a mapping table in main memory. Andy had designed a very clever MMU for the Sun 1 and the Sun 2, which no cache, but it would take low-order address bits and use them as RAS, and then have a RAM which translated higher-order address bits, higher-order virtual address to the physical address, and then sent to main memory. So a 2-stage MMU built out of RAM. Kind of hacky, but it worked. It gave a 0-cycle access memory to his 68,000 base systems. TLBs would be hard to implement in a gate array. So I said, hell, let's just stick with Andy's MMU, not make the MMU part of the architecture, because the MMU changes all the time, and it's part of the I/O architecture, which changes with every kernel and every machine, and it's not visible to the users. So it doesn't need to be part of the architecture. I mean, HP made the opposite decision on precision. They made a whole I/O architecture which constrains you, to whatever decisions you make then. So we did memory mapped I/O, gave it a separate address space identifier, lots of them, and made it totally under the architecture. And that was something I really pushed, and the OS people supported it. The OS people also noticed that 68,000 had a high interrupt latency, and SPARC solved that problem very nicely by giving the kernel new set of registers on kernel entry. So like I said, designing an instruction set architecture is like designing a home. I had to kind of stoically guard the fort against everyone's crazy ideas. The biggest person of crazy ideas was Bill Joy, who was talking to the Lisp people. They wanted a tagged architecture. So Bill would actually fight, I'll stop asking for X and Y if you give me Z. I would get so frustrated with him that you'd probably get reprimanded for this today, but in one of the architecture meetings, they actually whipped out a water pistol and shot him in the face with a water gun just to get him quiet down. It was so crazy. We did end up implementing a tagged add and tab subtract instruction for the Lisp guys. Later, the people at TI noticed there was a bug in them. I flew out there with my tail between my feet, realizing that we'd screwed it up. Because the tag bits, if added together, could overflow into the... So my heart wasn't into it, I guess, and those instructions were later deprecated. In the end, the Lisp people said, all we want is a fast clock rate and a large cache. So that just shows you how you can get wrapped up in instruction set design.
So what about floating point? How was that brought into the architecture?
Yeah, well, so I did design good floating point instructions. We had David Huff, who was a student of Kahn at Berkeley, and Kahn had created the IEEE floating point standard, essentially. And he had single precision, double precision, and extended precision, which is 68881 was going to do 80 bits of extended precision. David was adamant he wanted extended precision, that you really needed them in esoteric floating point algorithms. You wouldn't have to think so hard about falling out of range. So we did put them in the architecture, but they were never implemented on hardware. And I actually ran into David yesterday, and he agreed it's probably a bad idea because it was never implemented on hardware. One thing we did is I made the floating point coprocessor be essentially asynchronous. You would issue the floating point commands, and they'd come back later with an answer with register interlocking. And I decided at the same time to define a coprocessor interface where people could put all their crazy ideas, vector units or graphics or whatever. So I mirrored the floating point interface in the coprocessor interface, and that really put to bed. That gave people a place to do something if they wanted to later on, and kind of put all those less pressure off the instruction set. I also, kind of like run length encoding from information theory, designed the instruction set with a very tiny opcode space. So I took a quarter of all opcodes to be just a call instruction. This means you could branch or call a branch anywhere to memory in just one instruction in the address space, and then kept the encoding really small to discourage people from doing more stuff. They eventually used the coprocessor interface to add stuff, but that was a way to keep the design simple.
So let's see, at this point, the SPARC was a design. There was no implementation done yet, right?
Yeah, we were starting to look at the gate array.
Okay, so again, the gate array was the approach.
Yeah, and so we were starting to look at it, and we realized right off the bat that we could not have an integer multiply instruction because there weren't enough gates in the 20K gate array. 20 total, but usable was probably 15,000. There are more gates in an I/O pad today on a chip than there were in our gate array. So there's no room for an integer multiply instruction. So we did multiply step, where you just shift one bit at a time, shift and add. Compiler people were happy with that. No divide instruction. SPARC, those were added to SPARC V8 later. One question a lot of people had is, why do we stick with register windows? They don't exist in RISC today. You want to have a lot of registers so the compiler can take advantage of parallelism. Well, it was a very simple thing. I had a meeting one day, and in the room, there was Steve Munchnick on my right. No, he was on my left, and Dave Patterson was on the right. And we said, guys, are we going to do register windows or not? And Munchnick said, based on his experience at HP on their work, which he was very tight-lipped about, he said, well, if we're going to do high performance, we need a coloring algorithm for register allocation, and I'm going to need to hire 2 more people. Well, and Dave Patterson said, well, we have Windows that gets you most of that performance for free, dynamically. So I said, okay, easy decision. We're going to stick with Windows. And that's the way it went. And, you know, it was nice having a lot of registers. Later, Bill Joy came up with an idea, since we had a current window pointer separate from calls, we could kind of prefetch a the group of smaller 16 registers in advance and not be slowed down by a 300 register file. So, Dave, I once tried to change the condition code bits to something more practical, and Dave convinced me to stick with 68,000 condition code bits.
So let's see. So you gave an example of the multiply, and you couldn't fit it in, so you made a compromise. Did you actually implement the gate array version of the SPARC? Or
yes, that was the first.
That was the first one.
This was the first SPARC. Yeah,
okay, so
I'll talk about the schedule in a minute.
Yeah,
This was the first SPARC.
You're right. That's a chip.
And I'll bring the board up and look at it. Yeah. So one thing that happened during this time is I got this call from the No Such Agency, the NSA, and they said, meet us at a parking lot in Mountain View. And I said, well, how do I know who you are? They said, oh, you'll know. So I show up in this Mountain View parking lot, and there are these individuals who showed me their badges, worked for the NSA, and they said, we'd like you to consider adding a population count instruction to SPARC.
Population count.
Yeah, POP-C, because it's in the Cray machines and it was in other high-end machines. And I said, I don't want to do that. Affect the cycle time. I always remember anti-big business and big companies and the Vietnam War, I think. So I knew it was used for decoding, decrypting transmissions. I said, look, you can do population count in just a few instructions. Your cache effects and memory effects will be more important. I mean, that's one of the homework assignments I had as an undergraduate, write the smallest program to count the number of bits in a word, and I actually won. I wrote it smaller than the instructor had ever seen it. So I knew how few instructions you could do population count in, like just 7 or 8 instructions. And so I refused. They twisted my arm. They flew me to Bethesda, to the NSA headquarters. And that was pretty scary. Stand by me at all times. You ever walk away, the lights go off. And I said, well, I have to go to the bathroom. Okay. And then that's where I saw a big floor full of Xerox STAR workstations. The NSA could afford them. They make a lot of noise, so there was a lot of noise there. And I'll never forget, on the way out at the NSA headquarters, the guard asked to see my papers. We didn't have laptops back then, because he wanted to count them. I said, well, you didn't count them on the way in. That was really funny.
So they had heard about what Sun was working on?
Yeah, everyone knew that we were doing a RISC machine.
Okay,
and I guess that included the NSA. And companies would come to us pitching their machine. I don't know if I...
Yeah, you mentioned some of that. I mean, Motorola was doing their own RISC.
Oh, yeah, I need to talk about that. Yeah, there was... there was...
well, Motorola had
so right in the middle of this work, things, even though we're starting on the gate array, we have a document, it's 1980, it's 1986. Management was concerned whether we were doing the right thing. I mean, Sun was open, everyone else was closed, and we were based on open Unix, VME standards. We told people that if Sun ever disappeared, you could take your software to another company since it's Unix and run there. Of course, that really wasn't true. We made OS changes that made it specific, but it was a good story. So people were concerned. People would say to me, in fact, I think this was John Gilmore, if RISC is such a good idea, where is the RISC startup company? Because MIPS hadn't been founded yet, and they were founded a week later after that comment. People would say, we'll need the entire systems group, 3 people, to port the software to it. And another concern was, since everyone was doing RISC, we might get scooped You know, someone will come up with a better one. So MIPS was happening at the time. So management hedged their bet by having all the firms come visit us. So, you know, MIPS was maybe more at a higher level with Bill, but AT&T came by, Fairchild came by. They're doing a thing called Clipper. Inmos Transputer came by, Bell Labs came by, and then Motorola came by. So we spurred all the offers saying, thank you, we're doing our own. And Eric Schmidt said, I'm not sure if RISC is a good idea, but we're able to hire a lot of good people because we're doing a RISC chip. So it ended up, from his perspective, it was hiring attractive. So at Motorola, under Roger Ross and Mitch, architect was Mitch Alsop. Mitch had worked or was inspired by Denelcor's AGP or HEP machine, which was an architecture which was an early threaded architecture, had 3 independent streams running, so that if you went to main memory, since you have to wait a long time, just execute other instructions from the other stream. So really way ahead of its time. And he was designing their 88,000 RISC design, but we were not a multi-threaded MP company. You know, we all had uniprocessor applications. There was no way, so his cycle time was slower. Just having 3 streams running concurrently was too much complexity. I said, this isn't going to fly. And he wasn't willing to change to a simpler design. So, I mean, 88K did change and was produced. But at that time, we also invited them in to see the machine. So, let's see, it was Tom Gunther and Roger Ross. I guess that was a little later, so I'll get to that. So I'll get to that later. So we had Fujitsu's attention, but they also thought, who are you guys? A little scrappy startup? You want to do your own microprocessor and take on these big companies like Motorola with design teams of hundreds of people? Who do you think you are? And I think Howard Lee kind of helped convince them that maybe it would work. Andy Bechtolsheim took a wait-and-see attitude. He, again, since the timeline for the machine was high-end and expensive and years out, he didn't really follow it very closely. He wasn't against it, but it wasn't really his cup of tea. So Bill Van Loo had already decided on a virtual address cache, and that made things a real lever for us. So with a virtual address cache, I didn't have to go through a TLB, right? So we designed the integer unit and cache units such that the address bits came out of the gate array unregistered, just raw computed bits. And then I had an S374 Schottky register that latched the bits and then drove the 16 cache chips. So the CMOS chip gate array didn't have to drive the cache, and that also gave us a longer cache access time, right? Because I could have an early clock to the external register. So this enabled us to build a 16 megahertz single cycle cache, which was actually patented, the only single cycle cache ever patented. So by giving us the flexibility to design our own chip and system, really then and all the years later meant the most for SPARC. It wasn't so much the instruction set and the details of it. It was more that we had complete freedom to design an I/O interface. You know, later it was multi-processor shared memory coherency interfaces. You know, Andy's M-bus or memory bus. You know, so that is what was the true magic we got from doing our own chips, is we could design our own systems ahead of the Intel world.
Right, you do full flexibility.
Full flexibility in designing the system, and that was the one example of that. The virtual address cache offered some really interesting conundrums to the OS people, though. If you know, with a virtual memory, you can have 2 virtual addresses pointing to the same physical address. So, if, you know, processors might map them that way. So we said, well, they have to be equal modulo the cache size, because they have to go to the same location. And then on a cache miss, we would just then compare the physical addresses to see if they were the same. But those were the kind of tricks we had to do to keep the virtual address cache. And Bill Van Loo, who was working on the 6820-based system, knew that and had already established that. So that was some groundwork that made it easier for us. So the project was named Sunrise, nice logical name, the chipset. 2 gate arrays, the integer unit, like I said, designed by Anat and Masood, Anat Agarwal and Masood Namju. And the floating point control, they control the Waytech floating point chips. The 1164 and 1165 were designed by Don Jackson. And then I had responsibility for designing the CPU part of the card, which I have. So I'll have to show the Xerox cards later, which I forgot to show. So this was the SPARC CPU card in all its glory. So this is the integer unit chip gate array, 20,000 gate array, and this is the floating point control chip, and those are the Waytech 1164 and 1165 floating point chips. And this is the cache, and this is the MMU. So this is Andy's MMU and the 128 kilobyte cache and 16 chips. And this is number 1 board, right? So it's got all the red wires, the changes we had to make. And I actually used this board for many years at Sun as my main processor board. Bill Joy teased me a few years ago for the wires, but we didn't have a simulator really to simulate all the mixed signal and different types of chips. 22 V10s, I don't know if you remember that, made this board earlier. We had to use PALs back in the Xerox days. So this is the SPARC CPU part, and everything above the line here was I/O stuff that Ed Kelly designed. So the proms or the boot proms, the Ethernet interface, the time of day clock, the VME interface. I designed the main memory interface here. So
this board actually became part of a Sun product machine?
Yeah, so this board you could plug into the Sun. You could take a Sun 3200, which used the 68,000 base version of it, unplug it and plug this in and get a Sun 4200. And that was our low-risk way to
and what version of SPARC was that? B7?
B7, yeah.
Okay, because that was the first public product one.
Yeah, and I owned the architecture manual, which was reprinted years later. But I also had responsibility for doing this, so I was kind of busy, working. I used to work. There was one period of time I remember. I know this might sound strange, when I worked every day, including Saturdays and Sundays, past 3 a.m. for 6 months. And I'll never forget, I'd be upset if I ever arrived home after the morning newspaper arrived, which was 5 a.m. I figured that was late. And I remember once walking up to the front door of our house, like at 4 a.m., and I went out with my key card to open the front door, and I just showed you how
didn't know where you were.
Confused I was. In fact, everyone at Sun was working like that. No one had families. I don't think that was intentional. But people's schedule would start shifting. It's like we're used to more than a 24-hour day. So people would start coming in later each day and rotating around the clock. It was really weird. So.
So that was the first Sun machine that had.
But one thing I forgot to mention is, in '84, this is what really convinced me that we were onto the right thing. In my lab notebook, I did this little calculation. I calculated for a Motorola 68020, which is based on microcode inside. So it had. I took an instruction mix of 100 instructions, 10 writes, 40 reads, a certain number of branch instructions, and I calculated what I thought its cycles per instruction would be. And the 68020, assuming certain die-cache miss rates and 0 and 1 state memory, came out to 5.2 cycles per instruction. So 5.2 clock cycles to execute one average instruction for a program. Whereas RISC, wasn't called SPARC quite yet, with a 5% cache miss rate and write through and all kinds of assumptions, came out to a CPI of 1.6. And I knew that RISC didn't issue that many more instructions than CISC. So just the ratio of those two, it was already a factor of 3 or 4. So as soon as so I had a 70 nanosecond cycle time for SPARC then, so 8.8 MIPS for RISC versus 2.3 MIPS well, it's 2.7 MIPS for 68020. So 2.7 versus 8.8, my heart rate raced. I said, holy shit, Motorola's out of business. I truly was, that night when I did this calculation, I knew Motorola was doomed. And it happened.
It happened, yeah.
Lost their 68020 program. And it was all because they had done CISC. They had done a microcode-based machine.
So let's see again. You're thinking of the big picture. There was this an actual Sun product that had a SPARC in it.
Mm-hmm.
What did you call it? The 4200? Is that what it was?
4200.
Sorry, 4200.
Yeah.
And so what was the next step? So I know there was a big discussion about multiprocessors, and the feeling was you didn't need multiprocessors, right?
Well, before I get to that, I was just looking through my papers that I brought, and one thing that I had fun with the architecture is, I had fallen in love with the DEC PDP-10 architecture because I had designed by Gordon Bell, and in the DEC manuals, he was able to fit the entire instruction set on one piece of paper, with little diagrams that, move, extend, half word, to, obviously a microcoded machine with so many instructions. So when I did the SPARC architecture, I thought, in honor of that, we had to have the SPARC instruction set on one piece of paper.
Okay, you managed it. Even a sparser piece of paper.
Sparser piece of paper, right. And I showed this to Gordon later, and he got a laugh out of it.
So did you want to get into the multiprocessor? I mean, you had told me that.
Oh, I was going to do the schedule next.
Oh, okay.
So just like the project at Xerox had gone pretty fast, we were blamed for not moving that fast, but I don't know, I thought it was not too bad. So we started the instruction set architecture design in August of '84. The SPARC V1 was by December. We had the gate array and board design start by May of '85. We powered up the CPU in February of '86, and the very first IU came back in March of '86, and it had a stuck register in it, so it was kind of partially working. It came back in April. We booted multi-user Unix in June '86. Floating point chips came back in July. Second version of the chips booted Unix in December '86. We shipped the first alpha machine in March of '87 to Lucid, 1 year after the first chip, basically. I noticed that we were running integer apps 3x faster than the Sun 3200, so we met that objective. And then Sun 4 and SPARC were announced on 7/7/87 at the Hayden Planetarium in New York City. The marketing hype was pretty strong. The most powerful Sun the world has seen. At the Hayden Planetarium, they wanted to do it in New York City to get attention. We actually had many ISVs there with their programs all running on the SPARC machine. So, it was all our programs were written in C, so all they had to do is recompile them, and they just ran. And that really sent a strong message. Fujitsu reported a demand of 5,000 chips per month by the end of '87 and 15,000 chips per month by the end of '88. One thing that I had forgotten that. Okay, so there were two things before the announcement that happened. Three things actually. Well, so one thing that we did is we had a cycle accurate simulator that Will Brown wrote, and we had, since there was so much competition with us and MIPS, we could run, the only benchmark available at the time was called Drystone, which is a synthetic benchmark, and there was whetstones as well for floating point. We would run Drystones and get a number. And one day, through John Massey or something at MIPS, we heard this really impressive number from MIPS for Drystones. We said, how is that possible? And we realized, the compiler people realized that you could basically take all this code and eliminate it because it produced a constant, and just print the constant. So the compiler had done that. The MIPS compiler had not done all the work. It had just generated the answer instead. So that made me realize that the Drystones were a shitty benchmark. I mean, not only that, they fit in the cache, so they were just horrible. But there was pressure on us to not do SPARC because MIPS was doing better. And there was a time there in the middle where it looked like we could get canceled. And so I authored a memo on why SPARC would be able to hit 10 MIPS. It'd be 3 to 4 times better than the 68020. Steve Munchnick, who was constantly improving the portable C compiler, was a strong advocate for SPARC, and so we were saved by the neck of our teeth at that point. But then Wayne Rosen invited the 68000 and 8080K development execs from Motorola in, Tom Gunther and Roger Ross, into our lab to see the SPARC board running at 10 MIPS. I showed it to them, and they didn't think it was real. The 68K guys had the 68030 coming up next, and they knew it was going to be faster, and they just ignored it to their peril.
So they thought it was smoke and mirrors.
They thought it was smoke and mirrors. Well, we showed them running in the lab. So, anyways, one last thing that happened right before the announcement on July. You always announce things in advance and say they'll ship later, right? So the SPARC machines shipped later in '87. Although one went to Lucent early in '87. Manufacturing starts doing burn-in testing, right, where they put your systems in burn-in ovens. In fact, I didn't tell the story during the first month at Sun when I arrived. I followed a fire truck into the parking lot to see smoke pouring out from under my office. I thought, I left something on last night. And they had a burn-in machine under my office, which turned into a burn-up machine, which fried Sun's inventory for that month and almost canceled Sun, Deep Six Sun. But anyway, so we had all these SPARC machines in an oven, and they were getting random memory corruption errors. Memory was getting corrupted. Main memory was getting corrupted. So on July 4th, with the Blue Angels streaming overhead, we're in the lab trying to figure out why is main memory getting corrupted. Obviously your first thought is it's going to be a hardware problem, a problem with refresh maybe in the main memory, a cache problem, coherency problem. And Ed Kelly, a friend of mine who designed the other half of the card and another system himself later, looked at me and said, it's a software problem. And he brilliantly deduced that because all these systems were diskless, that was the only difference between them and a normal system. And so there was some problem associated with the diskless operating system. That was a big sigh of relief. Yeah. Oh, and then the other thing that happened is right after it went into manufacturing, there was this new company called Synopsys, which was doing gate array synthesis, and they had a static timing analysis tool, and they wanted a real live net list to test the timing on. So we gave them the Sun 4 board, and I'm like going, holy shit, I'm going to find out if I have any timing violations in this board, because there were no static timing analysis tools generally available in the open market. I mean, Xerox had one, IBM had one. Xerox had one, but Chuck didn't use it. IBM had one. There were none of that, but here was Synopsys, with one. And I'm like shitting bricks. And the next day, it came back with like one timing violation, which was the main cache path. It was all the loading of the 16 RAMs. It was 5 nanoseconds off. But luckily, just then, an SRAM came out that was 5 nanoseconds faster. So that got put in at the last minute. And then, after announcement in November '87, SPARC and the Sun 4 received Fortune Magazine's Product of the Year award. So I may be the only co-developer, hardware designer to receive Fortune Magazine's Product of the Year award twice.
Oh, very impressive.
Yeah, which is pretty funny. So after all these late nights of nonstop debugging, and I should mention, I mentioned that I married Robin in '84, and in '87, SPARC was announced and won the award, and that's when our son was born. So that was another fun thing that year. So after hours of all this nonstop debugging and production ramp up and presentations, I was pretty burned out. So Wayne Rosen started Sun Labs, the research arm of Sun at that time, and Ed Kelly and I were its first members. And Dave Ditzel soon arrived from Bell Labs. I spent this time to author a paper on SPARC for the spring ComCon conference in 1988. I attended a RISC panel session at the 14th Asilomar Microcomputer Workshop. And then I went to PARC, back to PARC, and gave a talk on SPARC. And it turns out that soon thereafter, Xerox adopted SPARC to be to run their viewpoint software. So I thought that was pretty cool. Also during this time, in September '87, Stan Baker of EE Times closed his restaurant for the night and invited people, techies from Apollo, HP, MIPS, and Sun, myself, to work on a new performance benchmark suite for workstations.
That's right, I was going to get there.
And I suggested we call it the Standard Performance Evaluation Cooperative, or SPEC, and the lawyers changed the cooperative because that's a legal term to corporation. And SPEC was born. So we accumulated a bunch of standard integer programs that didn't fit in caches, and solidified them, and that started the whole SPEC process. And that was music to everyone's ears, because then we had at least a half-realistic set of benchmarks instead of Drystone to base performance on. And then SPARC International was formed right before that, I guess. Sun announced a set of SPARC licensees to make it open, Cypress, LSI, and Bipolar Integrated Technology, or BIT. They did ECL stuff. LSI and Cypress embarked on 25 megahertz, full custom for Cypress, standard cell for LSI. The LSI chip came back first. Eventually 20 SPARC licensees were announced, actually. The Cypress thing was interesting because Joan Pendleton, who was part of our team then, really wanted to be the architect of the Cypress chip, but the Cypress people did not go along with that. And then Fujitsu came out with a 25 megahertz SPARC chip for the SPARC Station 1. So that was kind of interesting. So Andy had basically thought that SPARC was too far out, too expensive with the Sun 4200, and the Sun 4200 cost around $30,000, or maybe $80,000 today. But he started to think about a low-end system. Andy actually wanted to do a low-end system badly, but Bernie and other people did not think it was a good idea to do a low-cost system. He actually left Sun for a couple of weeks. And the founders of Sun said, not a good idea to have our founder leave, so they gave him a whole division called the Educational Division, and Steve Jobs was doing machines for the education market. So Andy was kind of competing with Steve, trying to get a low-cost entry point, worked on his own, did gate arrays with LSI logic, designed a thing called the S-Bus. S stood for school bus. The project was called Campus. He designed a complete system. He had to select a processor, and he had a choice, 68030 or SPARC. And Ed Kelly, my friend, basically met with him every day and said, SPARC is here, higher performance 68030, you should do SPARC. And over 2 months, convinced Andy to do SPARC. And so then, all of a sudden, our competition, Sun's competition, had inexpensive workstations. So all of a sudden, Andy was a hero. So he was folded back in, and his campus became SPARC Station 1 with the SPARC chip. And that's what really put SPARC on the map, with high volumes for a pizza-sized box that sits on your desk. And also at that time, we got this thick envelope in the mail, about 5 inches thick. IBM sent a whole stack of patents at us, saying, you little scrappy startup might want to look at these. And they were a complete set of patents for the IBM 801 RISC processor, and things like channel controllers for a 7090. If you did had a DMA chip in your system, you had to cross-license with IBM because they had invented the concept of DMA with channel controllers in the 1960s. Wow. And they also had a patent on backspace. If you did backspace in your user interface, because they had a backspace character on this electric typewriter. So this patent had a complete mechanical drawings of a electric typewriter and the schematic diagrams of channel controllers. So none of the RISC patents we violated, because 801 was different, separate instruction and data, but we cross-licensed anyways. The lawyers decided to cross-license with IBM anyways. And then in '88, we started development of an ECL with BIT SPARC chip and a high-end server.
And then next was SuperSPARC, wasn't it?
Oh yeah. So okay, here we are. So people were saying, if SPARC is such a good idea, where is the single chip implementation?
Because you had 2 gate arrays.
Yeah, we had gate arrays and an external cache. So
You
where's
had a lot of stuff, yeah.
Yeah, we had a lot of stuff. So where's the single chip? Well, so they hired the 386 design leads from Intel, Jim Slager and Jan Prack, who did the 386 at Intel. Many people worked on it, but they were the lead managers there. And this was going to be Sun's first full custom SPARC chip. The code name was Viking. SPARC International was formed by that time, so the control of the SPARC architecture was transferred to a separate company called SPARC International. Dave Ditzel had come from Bell Labs, and he was Sun's representative there, and became really the SPARC cheerleader. We added integer multiplying divide at that point. That became, because there was room for it now, that became SPARC V8. Texas Instruments was selected as the chip vendor, but they selected their bi-CMOS technology, bipolar devices with CMOS. And the design, the pipeline design, they were trying, we thought we, meaning myself and other people, were trying to do too much in a single cycle. They had flow-through latches and very aggressive pipeline. And they were having a hard time achieving this initial cycle time goal, which was just 33 megahertz pre-tape out. And it's like we created this little culture inside Sun that was foreign to the rest of us. It was kind of an alien management culture, closely guarded, circle the wagons, authoritarian. Jim Slager asserted full ownership of all CMOS design. Anand Agrawal, who would...
He was working on ECL at that
ECL, and had led the whole integer unit chip success. There was a falling off between the two. Jim didn't communicate with him, treated him like a nobody. So animosity grew between the teams. In the end, Viking ended up being 2 years late. And it almost sunk Sun. It caused us to fall behind in terms of the RISC rates. I mean, luckily people were buying Sun not so much for the RISC, but also for Sun OS, then called Solaris. I mean, people wanted Solaris. Solaris was extremely stable and reliable. It was the most stable Unix out there. We used to have contests to see how long you could have a machine go before you had to reboot it. My workstation never rebooted in a year. And we had people who ran servers for over a year and a half, never being rebooted. I mean, Sun OS was so stable. Viking was 2 years late. Scott McNeely later thought it was one of his 2 engineering mistakes, the other being combining Sun OS with AT&T's Unix. I even thought about leaving at that time. Dado Bonato, who had started S3, had done an Ethernet startup, started S3. He wanted to do a chip that would combine x86 and SPARC. He got a guy from NextGen, Greg Favor. I thought that was a bad idea, so he didn't do that. So there we were with Viking late, but all of a sudden in 1989, in the spring of '89, I was in one of the buildings, and all of a sudden, all you guys from Xerox showed up. In the hallways was Jean-Marc Freilog and Pradeep Sindhu,
who you had worked with,
who I'd worked with at PARC,
SPARC.
And they were like, I go, what are you guys doing here? And they had realized that they couldn't do the Dragon project on their own. I had left partly for that reason. And they decided to link up with Sun and do the chipset with us. And the project was renamed Sun Dragon. And for me personally, it was like, okay, this is kind of cool. Xerox, you adopted SPARC, and now you're putting my feet to the fire to finish the I/O chip that I hadn't done at PARC. So I ended up becoming manager of the I/O ASIC chip group for Sun Dragon. So we did 2 150,000 gate arrays with LSI. That was their high-end gate array. The interface between the packet-based Dragon bus, the system we designed had 2 of them, separate. You send out a request for a block from memory, you get it back later, packet-based, very high throughput, but very high latency. But we designed a board, 2 chips that would interface between those 2 guys and the S-Bus, which was Andy's
school bus,
which was like the PCIe bus. Intel announced a bus very similar to it called the PCIe a little bit later. Bill and Andy and I kind of thought about what the system board should look like, and I wasn't involved on the system board, but I later got one. But the vision that we had was this. So this was the massive SPARC Center 2000 board, or the first Sun Dragon system. So it had the two Dragon bus interfaces, and it had slots for 4 S-bus cards. And these were the ASICs that my group did. Well, let's see. And so it was a multi-layer board. You can see it stacked. The DRAM chips and 2 Viking chips. So the principle was you could scale performance as you plugged in up to 10 of these boards. You could get 20 processors. Each board had memory, processors, and I/O. So they kind of scaled as a unit. A very egalitarian concept. Of course, the problem was the system was very expensive. And my concern was there were no benchmarks that really showed it was worth doing, because it had high throughput, but the memory latency was so high that individual performance was low. Well, it turned out, years later, I'll talk about the details, this became the foundation for Sun's servers in the .com era. It was a good NFS server, so a good web server. And it helped propel Sun during the .com era. But at the time, it wasn't clear it was a great idea. But it worked.
Yeah, so that's multiprocessor. You had told me that the move to multiprocessor wasn't just a smooth thing.
Yes, no, it wasn't. Yeah, Bill and I were against multiprocessors for a long time, because with microprocessor performance doubling every 18 months, and it was easier to design the next 2x processor than to design a multiprocessor. So why would you waste your time designing a multiprocessor? I mean, the whole speed of evolution at that time was so fast. It's just hard to imagine. So finally, though, in one of our lunch debates, I remember kind of reminded me of Butler Lamson's debates in the cafeteria. Bill Joy would reign, over these debates at lunch. We realized that you could save on the power supplies. If you had a multiprocessor, you could have a common power supply of sorts, instead. So it was kind of an odd decision.
For any reason, yeah.
And that opened us up to working with Xerox on the Sun Dragon. Pradeep Sindhu authored a very complex asynchronous memory model, because you could get memory back at different times, which became part of SPARC v9, but I'm not sure anyone really used it. Intel did that many years later as well. So I was saying what happened to this history-wise. So a company called Floating Point Systems in Southern California decided to build a 4 Dragon bus, or XD bus as it was called, system. And they marketed that. We licensed it to them, and they marketed that as as their own machine. Cray bought them, Floating Point Systems, and Cray marketed it as the Cray CS6400. And then Silicon Graphics bought Cray in the early 90s, or mid 90s. And so now Silicon Graphics had MIPS and SPARC, so they sold that division back to Sun. And that became the Sun Enterprise 10,000 server right at the .com era. So that's what propelled Sun's growth during the .com era.
Okay.
So wow. this design that had started at PARC in 1983 or so, went to Sun, and then became the Sun SPARC Center 2000, went Floating Point Systems to Cray, back to Sun, and that was the machine that propelled Sun during the .com era. And Pradeep Sindhu, again, we were disappointed with the long latency and the throughput nature of the design, but Pradeep Sindhu took the design ideas and became the founding member of Juniper. And he took the ideas of the XD Dragon bus and built switches out of them, and became the founder, and eventually, or soon thereafter, I think, the CEO even of Juniper. So that's the Sun Dragon. So an ecosystem got canceled in late 1990. And people were engineers were kind of discouraged. Now, SPARC had started, fanfare, we were really high performance. Viking was late. This was high throughput, but not great for a workstation. People were looking for a silver bullet. So the engineers said, let's build SPARC, scalable architecture, new technology. Let's build a SPARC in gallium arsenide. You know, what Cray had tried to do with his Cray 4. So we linked up with Vitesse, and we started a team of about 20 or 30 engineers. Anat asked me to be manager of it, to design a gallium arsenide processor. 200 megahertz was our clock goal. And I was like, holy shit.
So that was the Brute project?
Yes, that was called Brute, yeah. And from September to 1990 to the June of 1991, I worked on this. And every week I would go into work thinking, this is going to be so cool. We're going to build a 200 megahertz gallium arsenide chip. But then by the end of the week, there'd be so many problems. So it had to be multiple chips, cache, integer units. So it had to be a multi-chip module. Made it expensive right there. Gallium arsenide has asymmetric transistors, it turns out. P-channel devices are much slower than N-channel devices. There's no memory, so you'd have to have ECL memory chips. So the number of problems and the challenges just kept rising and rising and rising, and the heat got hotter and hotter. And Viking's late delivery was hurting Sun's revenue and prestige. Something had to break. So Bill and Andy stepped in and said, this is crazy. So we redirected the gallium arsenide team, Anat's Echo team basically, and said, you guys are going to do a CMOS processor, and it's going to run in parallel with Viking. So you have two leapfrogging microprocessor programs, like what Intel does. Intel had a team up north, they have a team down here. They leapfrog each other. So Jim was not happy about that, but hey, that's the way it goes. So Anat was tickled pink. We get to start a real full custom CMOS design project. And but now the question is, you're about a year and a half to 2 years behind the market. How do you attract a design team when you're behind? So we had to go into, Anat asked me to be the second line manager for what became known as UltraSPARC, a 64-bit machine, a V9 machine, SPARC International. I guess I should comment on that. It was pretty easy to extend SPARC from a 32-bit architecture to 64 bits because I designed such a simple instruction set, or we had designed such a simple instruction set. Just make things 64 bits wide, basically. Although Bill Joy came in and realized that there should be a whole separate set of registers for the kernel, independent of the register windows. So he defined 3 separate sets of trap registers so that even the kernel could trap itself. He would command SPARC International meetings over the phone because he had such a incredible presence. So we started this work and we got into hiring mode. We had to hire over 120 people quickly. So we were interviewing over a dozen people a week. We would have joint hiring meetings on every Friday, how to build a team. And you find people who want to help save the ship. They who want to help, pull Sun out of the being behind. So a key person we found was the architect Les Cohen, who came from Intel to design the Intel 860, and he became the lead architect. I was responsible for the front-end design team, all the logic design and the verification. My team was divided into the prefetch and dispatch unit, the integer unit, the floating point graphics unit, the load store unit, and external cache unit, and responsibilities for the architecture, performance analysis, simulation, compilers, specs, logic design, diagnostics, circuit, and full chip static timing analysis and hardware emulation. And I grew the team from 12 to 80 engineers and had 6 first-level managers. And again, this allowed us to have full control over the interfaces. We designed a 16 kilobyte iCache, physical, 16 kilobyte dcache, a large external cache, 128 kilobytes, the UltraSPARC port architecture, UPA packet switch, non-blocking interconnect, so we could just glue the chips together to get a multiprocessor, just connect them together. 16 bytes wide, 600 megabytes per second bandwidth. One thing that happened, I remember, there was a really bitter taste about the cancellation of the gallium arsenide project. And the team wasn't so sure that going off and doing a CMOS thing would get us there. And one example of that was what to call the project. And the team, we had these names. I mean, what you call a project is important. And one name was Bob, which was clearly a reference to you-know-who. And the other name was Spitfire, that Nigel Ross from Great Britain had proposed. Obviously an important fighting machine during World War II. And when I came into this meeting, the team was stalemated. It was an equal vote for Bob and Spitfire. That just shows you how, disillusioned some of the people were. And so I cast the deciding vote
For Spitfire.
For Spitfire, yeah. And, that was a good symbol for the project, as a fighter. So we hired Les Cohen, I mentioned, and he had already, on the i860, had introduced some graphics instructions. So he designed SPARC's multimedia viz instruction set, to speed up media stuff. We were the first microprocessor of note to actually come out with an extended instruction set for multimedia. And Intel did later, kind of followed the example. And while we were struggling to ramp up, right in the middle of that, I was shocked to see that Fujitsu was funding a startup to do a SPARC microprocessor. I'm going, holy shit. We could hardly get funding enough people to save SPARC. And here's Fujitsu starting a company to do their own SPARC chip to outcompete us.
It was literally a licensed SPARC chip.
It was a license. Yeah, we licensed the technology, so they got a license.
Okay.
Wow.
And
And it was called HAL.
Oh, yeah.
The name was kind of funny. It was supposed to be named after Andy Heller, who was the founder of IBM, who pushed the RX 6000 through IBM, and Bernie LaCrue. But Bernie decided not to join, so the L ended up being. And their objective was to outdo IBM and outdo Sun and build workstations and servers to outperform IBM and Sun. And Fujitsu footed the bill to the tune of hundreds of millions of dollars. And I'm just going, holy crap. And so we had a competitor even. I mean, luckily, they did the second system syndrome. They designed a chipset that was too complex, too expensive, and too much hair. But I did got to know Winfried Wilke, who was head of engineering there on that project, who we later linked up with again. And Bob Montoya was actually an IBMer who was known for floating point. Actually first introduced me to the idea at a Hot Chips conference. He walked up to me with a pencil that said IBM and SPARC on it. And he said, yeah, those are the companies we're going to kill.
Oh, they were going to kill.
Or, by using SPARC. So how do you develop a whole new pipeline out of scratch? So you have this alternative of doing a very complex pipeline that tries to execute a lot of instructions in parallel versus a high clock rate pipeline with very simple. DEC was an example of that, and other companies are an example of more complex. So we built a microarchitecture pipeline simulator called Shade so we could test the efficacy of various pipeline trade-offs and just simulate them running programs. We'd run traces of the spec-int programs through the simulator to find out how they were doing. And we noticed that out-of-order execution didn't buy us very much. We thought it only bought us 30% performance gain. Well, if performance is doubling every 18 months, that's equivalent to about 4% per month or 1% per week. So if you're only going to get 30%, and it's obviously going to take more than 3 months to get that implemented. So, so my rule was if an architect had an idea for a new pipeline feature, he or she had to prove to me that he could define it, model it, implement it in the team, do the diagnostics, and debug it in under a week. since that didn't
That
happen.
was the criteria.
That was my criteria
moving forward.
for
on
moving
something.
forward with any new architecture idea.
Okay.
And so that you could really cut out a lot of stuff that way and remain focused on something more simple, process technology, which Ron Melanson pushed Texas Instrument on. You know, this was the first. This is before they got good at DSP chips. We basically pushed their technology. He kept pushing them. We need a faster transistor. We need a faster SRAM, you know. And that way, if our schedule slipped, we would just push TI a little harder, you know, to keep the cycle time up. So I like to, my analogy I like to give to designing a large microprocessor, it's like designing a large city. Like, let's take like San Jose. So imagine, Roy, you're told to design San Jose from the ground up. And really, I think the size of the effort is comparable. And the criteria is everyone has to get from all their homes to their office within 1 hour. So you have to design all the highways, freeways, buildings, office, everything to move everyone within 1 clock tick. And if anyone is late, the design doesn't work. So you have to get a team of 120 to 300, 130 people to all work together on this common goal of meeting the cycle time and correct functionality. So the cycle time work trades off against functionality. You make enhancements to improve the cycle time, which then makes the design more complex, which introduces bugs. So once you launch the thing, it's like a rocket. You can't really change it much afterwards. So we decided, Guillermo Maturana decided to develop a cycle-accurate simulator in C++, which we ran against the netlist, which was in Verilog, and that became the de facto spec. The actual written spec for UltraSPARC was 800 pages of English. You know, so you could misinterpret maybe what the spec is saying, right? 800 pages, and so we made the cycle-accurate simulator be the spec. So if the simulation of, you know, traces against the Verilog ever miscompared, you could say, well, is it a problem in the spec or is it a problem in the design? You know, most of the time it was a problem in the design, but you had this check. And because it was cycle accurate, you could detect timing problems. So for instance, you would have we had a bit, everyone does this, you know, to be a predictor bit on branch prediction, right? Well, if it's wrong, you'll still branch. Well, we realized through a miscompare that one benchmark was running 30% slower because the branch misprediction logic had a bug in it. And the whole chip would have run 30% slower if we hadn't, on that benchmark, if we hadn't had the cycle-accurate simulator.
Mm-hmm.
So that was
very
really
useful.
important. It ran about 6,000 instructions per second, 600 times faster than the Verilog as well. So you could run a lot. He found 65 bugs. We actually booted Solaris and open Windows on the cycle-accurate simulator, and found 65 bugs, 30 functional and 35 performance-related bugs. And we also got Spec 92 estimates by sampling 1/3% of the traces. So we actually knew our spec numbers before the chip taped out, which is kind of scary because you're hearing numbers from other companies at the same time. So my main point was the diagnostic team was as important as the architecture and RTL design team. They wrote 1,500 diagnostic tests, 1,500. And each diagnostic on average uncovered one bug in the design. So I could do a chart that showed the number of diagnostic tests planned, the numbers implemented, and I knew that each one would correspond to a bug. And so, you know, we keep pushing to get more diags written. If you stop, you know, maybe you'd fool yourself, but I could then predict when tape out would be. You know, when we finished all the diagnostic tests, the last bug would be right before tape out. You know, later someone told me that at Microsoft they send all the software testers to a movie two days before release, so there won't be any bugs at the last minute. We also wrote a 100,000-line pseudo-random diagnostic generator that generated 1 billion simulation cycles, so just random collection of instructions, and we could compare them against the cycle-accurate simulator to see if there are any bugs. We also simulated up to 4 UltraSPARCs running concurrently, so that we knew the MP stuff would work right out the chute.
This is all using the cycle accurate simulator.
We also had a huge simulation farm. We had a server farm that numbered over 220 SPARC stations, or 500 processors total, 2 terabytes of storage. We had our own resource allocation manager, which had rules for policies for running simulations and diagnostics. We had to develop 100,000 line CAD flows, integrate tools from different EDA vendors, Mentor Graphics, Synopsys, Cadence, Chronologic, in-house developers. We had 150 concurrent users of the server farm. We also had to do design for manufacturability, which is also part of the gate array. You know, how do you have serial tests in the chip to make sure the chips work before they come back? And one of the discipline things we did is we had a synchronous or a lockstep release cycle where every week we integrated the entire net list, ran the diagnostics, and reported the bugs to people Friday night. So on Saturday, they knew what they had to fix. People didn't go home on Saturdays or Sundays. So we integrated on Friday, ran the diagnostics overnight, the failing units were reported on Saturday, and hopefully by Monday or Tuesday they were fixed.
They're fixed, yeah, 24/7.
This kind of constant wheel release cycle. Now the other thing we did is we did hardware emulation of the net list. We got what's the name of that company? It'll come to me in a minute. But anyway, so we did 10 complete integrations and virtual tapeouts before release. We did static timing analysis tools via Perl, which was a parsec software tool. RC delays were a big deal. Piyush Patel ran that. Initially, 8% of the paths were 2x over timing targets. So imagine you're actually running half speed initially. 10% of all paths are half speed. So you can imagine all the work on the... My analogy was just like cramming steel wool into a box. You know, you push it down here and something pops up over there. So you start to worry whether the box is too small, there's too much steel wool. And you just don't know, you know, when you're designing the chip.
Yeah.
QuickTurn. QuickTurn was the name of the hardware emulator. So the CAD team had to take the Verilog netlist, convert it into the software for the QuickTurn emulator, which mapped it into PGAs, which then ran the netlist at a hardware emulation speed. So that was like a complete release of the chip. So everyone kind of hated it, but it had to be perfect. So that created a lot of discipline. And it did find one bug, in the gate net list. So there were 2 sets of teams. I had the front end team, and then there was a circuit design team, circuits and libraries, and Hem Hingar from National Semiconductor ran that. And this was like 2 cultures, where they were all the nose to the grindstone circuit designers, and we were the frou-frou logic designers and architects. So Hem and our job was to try to get these 2 teams to work as one. And this is where I learned that that just listening to people was really important. You know, if people there were a lot of arguments between people and personality conflicts and disagreements about the approaches we were taking. So we would have gripe sessions every Friday. You know, you'd get 20 or 30 people in a room, and we'd let them ask us anything they had on their mind. You know, what were they unhappy about? You know, me, not him, people, schedule, and we'd write down the main points, and we'd write down recommended changes, and we always couldn't implement the changes people asked for, but just the fact that we listened to them really made a difference. People said, well, you guys really, as a management team, you care because you're listening to us. Yeah. And that's one thing we really learned. You know, we started providing free meals. You know, this is a common phenomenon at the chip companies at the time. Anat said, though, you had to work at least an hour after the free meal before you could have it. So in Hem's group, Lavi Lev and Andy Charnas led a disciplined circuit methodology. Lavi had a 200 entry checklist for the circuit designers, 200 items he had to sign off on. 200 per circuits. There were typically 4 design reviews per block, 13 simulation corners, and HSPICE verification. He drove less than 5% clock skew across the chip. Power grid analysis. They put a 100 nanofarad capacitor on the chip. Ron Melanson established a co-management team with Texas Instruments on the process and technology rules, pushed the design rules to meet our faster clock weight needs. I mean, it was truly a lot of work to get 150 people to all work together to get something out. Intel had even bigger teams. And I just, usually they gave each young graduate a little piece of the chip and said, you design that, and you burn out after 2 years. So we had this tension between what we call the tall, thin designers, expertise in logic, circuit, and CAD, versus siloed horizontal engineers. We just tried to break that down. And I think that tension was there starting with Meade Conway, because I don't think Lynn Conway really understood how hard it is to design circuits that truly work across all process corners and meet the goals you have. And so we were kind of combining them together as a new team, so it was very difficult. So on the schedule, our first chip integration was in 1993. First silicon was in September 94. Unix booted the same month, right? First silicon came back and Unix booted because we had simulated it all. The UltraSPARC Ultra 1 workstation FCS to 1 year later in November 95. The chip, I have a picture of it somewhere. The chip, we all got these little things. So now you can hold 5.3 million transistors in your pocket. I think I have one in my pocket. Yeah. So 5.3 million transistors. So what used to fit on the board and now fits in your pocket. Of course, now we're up to 1 billion transistors, but the chip sizes have remained about the same size. So you see all the parts, the caches. 4-way superscalar, 9 functional units, half micron technology, 4 meta layers, 5.4 million transistors, and taped out September 94. So we were very proud of this chip.
Yeah,
we had gone from gate arrays to a late project to a successful project, which put Sun back on par with the other RISC vendors at that point. And we had systems that people wanted, that ran Solaris. There were 300,000 lines of Verilog. So now you've kind of lost touch with gate design, because you just write Verilog statements and all the gate design is done by the Verilog compiler. 5 million lines of diagnostic code written, 5 million lines of code were written, diagnostic code, 2 billion simulation cycles. We estimated it cost $60 million and 300 person years to do the chip. And the initial chip had no circuit bugs, and it met the speed goals. So we were really, really proud of UltraSPARC. And so in December 94, our Marcom person, she got together an event called the Making of UltraSPARC to company analysts and industry people. And one thing that I noticed was that if you looked at in this chart, I did this internally, I guess, in December 94 to start with. If you did a plot of the spec int rate and the year of various chips, no, this was at the Making of UltraSPARC. This was the public talk. You had a 6 MIPS chip and a 10 MIPS, the first SPARC chip, and then 22 MIPS, and you had a straight line of 50% average growth per year. And a few years later, I filled in the names of the systems. MIPS, Sun, IBM RS6000, SGI, HP, DEC, IBM 9000, DEC. But the line was going up at 50% per year, and the question is, will it keep doing that? Does an explosion last forever? And what I noticed is that there was no single technique that was leading to these numbers. It wasn't just pure clock rate, it wasn't pure pipeline design. The 60% per year speed up, 21% per year was the microarchitecture and the compiler, 32% per year was the clock rate, 20% was process, and 10% was circuits. So everyone thought that this was Moore's law, that microprocessors double in performance 18 months. It's not Moore's law. Moore's law was the number of transistors double on a chip, and that just gives you the clock rate increase at 32% per year, kind of the square root of 2 every year. And you also, to stay on this line, have to improve your pipeline and improve your compilers, or you fall off the line. So the question was, how, from 1996, to stay on the line? You would have to, this was instructions per cycle now, go from 1.2 instructions per cycle in 96 to 2.6 by the year 2002 to 12 instructions per cycle by the year 2008 to stay on the line.
But those are actual
No,
points.
these are futures. This was done in 1995. I'm just saying
okay.
that to stay on the line,
Yeah, that's what you had to do,
you
right?
had to have an incredible instruction level parallelism, and you had to have 12 gigahertz part by 2006. And that didn't seem likely to me. The next year at a VLSI technology seminar, I did a more detailed mapping of CPI and spec int. So what's remarkable is the performance. This is the cycles per instruction. It varies a lot, but the performance follows this line. So there's no magic recipe between clock rate and pipeline complexity and compilers. Everyone's stuck on this line. It's not Moore's law. Maybe it's Gordon Bell's law or Bill Joy's law or my law, but and floating point did the same thing. And so then I projected in 2005 how it would slow down, because I knew it couldn't continue. So if the clock rate were to continue at the rate it had been historically under Moore's law, by 2010, the clock rate would have been 40 gigahertz. Today, it would be like 800 gigahertz. So where's our 800 gigahertz uniprocessor? It hasn't happened. And then, so the clock rate I predicted would hit 6 gigahertz in 2010. So back in 1996, I predicted, and that's about what happened. Someone got a 5 or 6 gigahertz clock, but nothing faster since then. And the spec performance number, I said, would level off. It would flatten off, and that's what it's done. And I've gone back and looked at these numbers. So the other thing that happened is that Intel started to catch up with RISC. So in what year was it? In 1996, a 200 megahertz Pentium 1 was gaining on a 200 megahertz UltraSPARC. So the 200 megahertz Pentium was 5 spec int, and we were 6.9. But by the end of 97, a 300 megahertz Pentium 2 eclipsed our 300 megahertz UltraSPARC 2. They were 11.7, we were 10.5. So it was clear there was no magic, fundamental magic behind RISC per se. That you could apply RISC ideas, improve your compiler, maybe do register renaming to get more registers in hardware, do good branch prediction, do a hardwired machine, no microcode in sight. That's the key point, is no microcode. So, so the talk I gave and at the time was the only difference fundamentally, and I think Dave Patterson has come around to this, between what he called CISC and what he called RISC, was CISC was microcoded and CISC is hardwired with lots of registers or registry naming and good compilers. And microcode started with Maurice Wilkes in 1951, and MIT Whirlwind in 1947. It was a regular array of diode array for control. You'd have two matrices, and you would just have diodes that would tell you what to do. And Wilkes himself was against using SRAM for this. It should be a diode array, basically, to simplify the control circuits. And what happened is people made it SRAM, and got carried away, right? We can change the instruction set, we can add features at the last minute. Well, and then, you know, the Mythical Man Month, IBMers, Fred Brooks at IBM really liked microcode and control store. So they designed the 360 line, you know, to go from 10x performance range, but it was all shifted down to performance. They didn't tell people. I talked to Fred Brooks many times over the last several years, and he told the designers there that if you could prove that a hardwired design was 30% faster than a microcoded design, you could do hardwired. But the microcoded designs were always the same speed as the hardwired because they were limited by main memory. There were no caches. Now, the high-end IBM machines had caches, but they were hardwired and caches and ran fast. But the microcoded machines were limited by main memory. So it was okay to have microcode in that sense because you were limited by main memory. So as soon as a cache came along, essentially replacing the micro store, voila, microcode's in the way. And so I like to, if I show my Dandelion card, the STAR card. So this is the CPU card for the Dandelion of the Xerox STAR. So those are the 4 2901 bit slices. And there's the 4K entry, 48-bit wide control store. Well, we saw the Sun board, right? It's just got gate arrays instead of 2901s, and it's got a cache. So all we did is we took these SRAM chips and turned them into a cache. And this had 137 megahertz cycle time, right? Which is not too bad. The first SPARC was 16 megahertz. So just get rid of just turn the microcode store into a cache array.
Yeah, that's a good way of looking at it.
And that's the difference between CISC and RISC, and that's it. Obviously, the instructions are simple. You don't need these really wide micro words. Oh, by the way, I hadn't shown this. This is the Ethernet card from the Dandelion. This is the chips right here to implement the FIFO, and this is Ron Crane's phase lock loop section right there with a 20 megahertz crystal divided by 2. This was the low-speed printer interface. I can't remember who did that.
Yeah, I don't remember.
You know. But so this explanation for RISC versus CISC, in my mind, makes a lot of sense. And you know, so I was starting to kind of think about these bigger level issues, getting more involved in the Computer History Museum. One thing that happened is in 1998, we presented the Dandelion hardware at the final demo of the Xerox STAR. I don't know if you remember that at PARC. And also at that time, I had heard that Dave Patterson had worked with IBM in some way. And you know, as a young kid, I always thought brilliant people got ideas that fell right out of the sky into their head. But you know, David interfaced somehow with IBM. So I got up the nerve in 1998 to call John Cock, the designer of the IBM 801. The RISC machine wasn't called RISC by him. I reached him at his home and I said, John, I understand that Dave Patterson may have somehow consulted with IBM. And he said, yes. I came out to California and I met with Dave Patterson, Dave Ditzel, and George Taylor every week at the local pizza place. And I just told him everything. I said, that's interesting. So I called Dave Patterson. I said, Dave, I just talked to John. And he told me this. He goes, yeah. And then a little bit late, because Dave had been really closed-mouthed about it before. And later, in 2003, the CHM did a 25 years of Hennessy and Patterson retrospective on their lives on Dave Patterson and John Hennessy, who was then head of Stanford. And Dave jokingly confirmed that John Cock had met with him and told him everything, and John Hennessy said, well, not quite everything. So what John Cock realized is IBM was not going to bring it to market because it threatened its 360 line too much. And the best way because he was in research, to bring it to the world would be to leave IBM, go tell everybody about it, which then caused everyone else to do one, which then pressured IBM to get its act together and do a good job. You know, Andy Heller drove the RS-6000 efforts inside IBM, and they did a good job. They're, you know, the various IBM implementations got better and better and better. So his algorithm worked. And I did an oral history in the 801 team a few years ago, and they, the manager confirmed that's what they did.
Confirmed that, yeah.
By the way, one comment again on the 360 was from Fred Brooks. I told you, he said he gave people the option to design a machine either way, hardwired or a control store. And one of the machines I learned, the Model 360 Model 60, or the NPL 400, was actually first built as a hardwired machine. And it was a machine Bob Evans was standing in front of when they announced the IBM 360 in 1964. But it shipped as a microcoded machine. So they actually changed it from a hardwired machine that was working to a microcoded machine. So it's the only computer I know of built on the same technology both ways. So I tried to figure out who the manager of the project was, and I eventually was able to find him and contact him. His name was Stu Tucker. Talked to him on the phone. He told me the performance of the two models was identical, which makes sense because it was made memory limited. So, but that's the only machine I know of that was actually implemented both ways, microcoded and hardwired. So my last comments on SPARC. I should say. Yeah, then I'll talk about other stuff. But one thing that happened is in November 1996, Comdex had an event, the 25 Years of Industry Achievement in Las Vegas, and the committee selected 7 micros for being, quote, seminal in nature and incredibly innovative for their time. And the ones they nominated were the 6502, the Z80, the 8088, 68000, the Intel 386, SPARC, and Pentium. Bill Joy didn't want to go, so I accepted the award for SPARC. I was a little intimidated standing alongside people like Federico Fagan and Andy Grove and Masayoshi Shima and John Crawford and stuff. But yeah, it was a fun event. I was the only person. I was only one of 2 people who didn't wear a tuxedo, so I kind of stand out in the picture. I figured we were rebel rousers, so why would I get a tuxedo? But anyways, it was a fun event in Las Vegas, complete with go-go dancers at the end.
So let's see. So where are we in terms of where you were at Sun? Was that close to when you decided to leave Sun?
Yeah, well, not quite. Yeah, not quite. So I was the program committee of hot ships. So here, okay. So we caught back up on performance, and we were as good as anybody else on performance. But what were we going to do next? So I organized an off-site workshop at Asilomar, where we had Bill Joy and Michael Deering, who was the graphics distinguished engineer at Sun. And we wanted to try to figure out a way to give Sun a boost in hardware. And we said, well, let's incorporate the graphics pipeline in the CPU. And so we went off and did that. And we said, oh, and since Java is here, and Java has just-in-time compilers and can compile to any instruction set, let's come up with a whole new instruction set. Doesn't have to be SPARC compatible. Let's be crazy and be bold again. And so we started, after 2 days of discussions and walks on the beach, we decided to do new ideas, a new multi-core, multi-threaded, simplified VLIW, speculative execution architecture that would run just-in-time compilers of Java code. You know, I wasn't the architect, but I was asked to be the director of the project. Andrei Kowalczyk was the second-level manager. The team grew to 50 engineers and 4 managers doing this whole new chip. The architect was, I forgot his name also at the moment. And it was called UltraJava, and renamed to Magic, M-A-J-C. And it was the first chip produced that really had a multi-core, multi-threaded model. So it could run. The idea was if you're going off to caches now, second-level cache is now getting far away at these high clock rates. So let's run something else under it, right? So multi-threaded and multi-core. we couldn't find room for the rendering engine on the chip, so we kicked that out, just made it the front end of graphics. And then I tried to find out who could use it. Well, Deering could use it in the graphics group, but we went to Sega in Japan and all these game companies, and we said, we got this hot new chip, and do you want it? And we said, and you program it in Java, and they just looked at us and laughed because they knew Java wouldn't be a great environment. So the chip was built, it came out, it worked. It was used in 2 of Sun's XVR workstation graphics accelerators, but never went anywhere after that.
So it actually made it into a product?
Yeah, it actually made it into a product, but it was a big cost for not making it
didn't go
in the real
further.
world. So after Magic started, while Magic was going on, actually, I was in an executive meeting, and Ed Zanders, who was head of Sun at the time, started thinking how we could capitalize on Java more, and Bill asked me, how big would the Mesa processor be if we implemented it in Silicon? And I said, a few microns on the side, and he goes, okay. So we're going to implement Java directly in Silicon. And that's how the project started. It was called PicoJava. The marketing people made a press release by Monday how big and beautiful it would be. And I'm going, we haven't even hired a team. So other people hired the team. I didn't like the idea because Java was meant to run on any instruction set architecture, not just a hardwired chip. And so we were kind of derided by the press for having done this. And I was able to haul Bill Joy up in front of the press. And I actually gave the presentation at the Microprocessor Forum on PicoJava, just because I wanted to have the experience of talking there on a very controversial topic. But that was an interesting start. And then while Magic was in mid-stride, Bill and Andy asked me to start a Java software project to give another boost to Java. And it was called Genie. And the idea was Bill had this kind of crazy dreamlike idea that computers could be formed by components just magically meeting up with each other and exchanging code for what their interfaces would be. And it used Java's remote method invocation. So the device drivers, today in an operating system you have to have a device driver for every type of device you have, and there has to be a rigid, these are the bits we're going to pass between each other. His idea was you send the code to do printing to the computer. You don't have a device driver with a low-level interface. You just send code around, because Java can send code around. Right. And that would make it much better. Well, the defect with that vision is eventually you have to talk to hardware. So eventually that code has to understand the hardware. But we had a big project. We built imitation Genie devices running diskless Suns and keyboards and monitors. And later I found that someone actually built a Genie device at IBM Almaden Research Center. But it was mainly a hype thing. So during that time, with Intel catching up and we're getting eaten from below by Intel and Intel compatibles, and people are now designing their own multiprocessor systems. I decided it was time to leave Sun. So I left in 1998.
98, okay.
And that's where I think we can leave things. And yeah, again, I like to say that one of the main, and then SPARC eventually got an IEEE milestone award in year 2015, driven by the guys at Oracle. I actually wrote the text for the plaque, but that was kind of nice. I don't know if I showed all my pictures. Let's see. So the original SPARC team, I didn't show this picture. So this was the original Dandelion team.
Yes.
So that was the picture that Bob Belleville, I guess he took it for Bob Belleville. That's me. There's Ron Crane. There's you, Roy. That was the guy from
Dick Snow.
There's Don Charlie. Jim Cuccinetti, and
Neil Hansen.
Neil Hansen were the two technicians, and Nora
Liddell.
Agawa or something like that.
Agawa was her maiden name.
Yeah,
yes.
yeah. So that was our whole team.
That's right. 1979.
Yeah. And then this was the SPARC architecture team, and Bill Joyce Ferrari. So there was me, Dave Patterson, Steve Munchnick, Anat Agarwal, Will Brown, Faye Briggs, Joan Pendleton, Don Jackson did the floating point. Goldberg, who helped me, in the OS group. Masood Namju did the integer unit with Anant. Richard Tuck in the compiler group, and I forgot his name. Dave Weaver in the compiler group took over the architecture manual from me, and Wayne Rosing, who became the manager of the group. Wayne, great manager to work for. He actually had managed the Lisa program at Apple before he came to Sun. He was a deck before that.
I remember that.
So I've worked for managers who both managed the Lisa program and the Macintosh program. Wayne was a great manager. He did quite well at Sun, retired, and then went to Google and did quite well at Google. So that was that team. And then if you count the rest of the team, you get the whole team was in this picture. That's a little small, so it'd be later. But this includes the rest of the software people. But still, it was a pretty small group. And this was the Fortune magazine award.